I would like to welcome everybody to this second blog. The blog is devoted to observations and also to discussion of supernova cosmology, including discussion on effects affecting dark energy determination and also on the Hubble constant. We will have first three speakers, and then a short coffee break, and then another three speakers, and then general discussion and a round table. And our first speaker is Ryan Foley. So thank you very much, Ryan, for being with us. If you want, you can start sharing your screen and start the talk.
I think you have to, okay.
And I can perhaps give everyone a 2-minute heads up.
Yeah.
To keep an eye on the time. I can do that easily.
Great. Okay. Well, thank you all. Today I'm going to try to set the stage for some of the later talks too, talk about supernova cosmology over the current decade. I'm Ryan Foley from UC Santa Cruz, and I have a whole bunch of collaborators. In fact, what I listed here is not everybody. But I wanted to highlight first in kind of this yellow gold are all the students and postdocs, because so much of this work has been done by them. And in red, I've highlighted 3 people at UC Santa Cruz who've specifically done a lot of work that I'm going to be presenting today. David Jones is an Einstein Fellow here. He's on the job market. You should hire him. He's fantastic. Phil Macias is a postdoc working on Roman things, and Matt Sievert's a finishing grad student. So if you're looking for an excellent postdoc, you should hire him. All right, to jump in, and I know we are in the white dwarf explosion session, but I thought it would be worth taking a moment to just say that type 1a supernovae are exploding white dwarfs. They come from binary systems where there's at least one white dwarf in the system. They accrete matter until they ignite their carbon. When they explode, they're very, very luminous, and that's all the white dwarf physics that you really need to know for the rest of the talk. When they explode, they have this characteristic rise and fade, and that's primarily dictated by how much radioactive nickel is produced in the explosion. That part you don't really need to know about, but what you should remember is that there's a relationship between how quickly the supernova rises and fades and its luminosity. What that means is that if you can measure the decline rate or the light curve shape, you can estimate the peak luminosity, and from that you can determine a distance. Now, when you make that correction and some other corrections, including, for instance, color corrections, you can significantly improve the distance estimate. So here I'm showing 2 Hubble diagrams with the same supernovae. On the top is a Hubble diagram where you just treat every supernova as a standard candle. There's quite a bit of scatter in this Hubble diagram. The distance precision is only something like 20%. And then if you apply these additional corrections for light curve shape and color, you can improve the scatter significantly, making the distance estimates something like 9% if you're using data in the optical. You can do even better than that if you move to the infrared. Okay, so from there, you can just observe a bunch of supernovae. And of course, there's a lot of work involved, but you can continue to build up these Hubble diagrams. In particular, here is a very recent Hubble diagram from the Pantheon sample. This has roughly 1,000 type 1a supernovae on it, from redshift 1 to a little over redshift 2. On the bottom here, you can see a residual plot, these Hubble residuals, relative to the best fitting cosmological model, which for this case happens to be very similar to lambda CDM. I'll get into some detail about this in a minute, but what I wanted to just point out is that the exact measurements in the Hubble diagram tells you about the content of the universe. And in particular, I'm going to right now focus on the details of what's going on with dark energy. We can parameterize dark energy as something that maybe changes with redshift. So you can talk about its equation of state and how that can evolve with redshift. We do this with 2 parameters, W0, the equation of state at redshift 0, and then WA, some kind of indication of how things are changing. And so if you had a cosmological constant, you would have W0 of -1, WA of 0, which is where these two dashed lines intersect in the center of this plot. And then here in red are the constraints from that 1,000 supernova Hubble diagram. And you can see that it's consistent with lambda CDM, but perhaps you can tell by the fact that the contours are going off the range of this plot, that even though this is really good, excellent work, it also needs a lot of additional constraints so that we can really try to rule out or rule in specific cosmological models. So at the top here, I've listed the values that we have as of roughly today. And for the aficionados here, I'm also listing the figure of merit, which is related to the size of these contours. A larger number is better. We are currently something at like 65. Good, but not great. So as has been the case now for roughly 2 decades, the systematic uncertainties for the cosmological measurements are similar to the statistical uncertainties. They've kind of decreased in lockstep. But the way to make progress here, it means because your systematic's limited, that you always have to attack the large systematic uncertainties. And here I'm showing the systematic uncertainty budget that we had from that Pantheon sample, that 1,000 supernova sample. And you can see it's spread out into a bunch of different things. And there are a lot of different things that you have to worry about here. There are calibration issues that are listed near on at the bottom. There are some supernova physics things, like the bias correction is related to the exact selection effect. There are methodology aspects like the SALT-2 calibration that's really telling you about the supernova model for people who don't know what SALT-2 is. There's some other intervening things like what's happening with the Milky Way dust. They're all contributing to this systematic uncertainty budget, and we need to make improvements in a lot of ways. But one of the things that we've noticed is that although this Hubble diagram looks really nice, you'll see that for the high redshift sample, we are really only using things that have been observed in the last, well, mostly last kind of like 10, 15 years. And this Hubble diagram does not include the groundbreaking discovery supernovae that were used to find the accelerating universe now almost 25 years ago. Those supernovae are not included at high redshift because we have these really well-calibrated, large systematic samples for high redshift supernovae. And so we don't need to include those small samples that might have some additional errors in them. However, at the low redshift end, below redshifts of 0.1, we are still reliant on supernovae that go back to the early 90s. And while this is incredible work, hard work, there are multiple graduate theses that have gone into this work. There are a lot of issues with this, from technical ones related to how the data were obtained, and now we like these instruments don't exist, so you can't really recalibrate the data properly. To other things like supernova searches in the local universe previously were targeted for very big nearby galaxies, and they found a lot of supernovae that way, but it also biases the kinds of supernovae that you find relative to what we find at high redshift, where you use an untargeted search. So we've decided to tackle that problem in particular because when you look at the uncertainty budget, this big slice, this Pac-Man slice that takes about 3/4 of the uncertainty budget, that is really dominated by that low redshift sample. So that's one of the things that we really wanted to aim for. And one of the great things about this is that those old samples, it took a really long time to build them up. To get to even 100 supernovae took several years. But that's because the discovery rate back in the 90s was relatively small. Nowadays, we are discovering almost 20,000 supernovae a year. And in fact, this plot here on a linear scale going all the way back to the first extragalactic supernova found back in 1885 doesn't do it justice. If you go into a logarithmic scale, you can kind of see the revolution that we're going through right now, where for decades, Fritz Zwicky and collaborators we're finding a dozen or maybe 24 supernovae a year, right around the time of 87A, and then of course the accelerating universe, and a lot of the work by people who are on the call. Things have just been kind of going up, almost doubling every year since. So you can take advantage of that because there are so many supernovae now that you can just follow hundreds every year now in really good detail. So my team has done this with 2 different surveys, the Foundation Supernova Survey using the Pan-STARRS telescope and the SWOPE Supernova Survey using the SWOPE telescope at Las Campanas. With both of these, we've built up samples of hundreds of type 1a supernovae. This has been published in a paper from a few years ago, and then the upcoming data sets will be published hopefully this year. We are really trying hard to do that. This is a relatively recent Hubble diagram showing some of this. We have even more data. We have over 500 supernovae observed through these 2 systems. In addition to having a really well produced Hubble diagram in these intermediate redshifts, sort of in the Hubble flow out to redshift 0.1, really good for doing dark energy work. We also are adding a significant number of very nearby supernovae that can be used to calibrate the supernova luminosity and be used for the Hubble constant, which some other people are going to be talking about later. So this worked really well, and we were able to reduce this uncertainty budget significantly. So on the left was what I showed before. On the right is after replacing the low redshift sample with this new sample. And overall, the circle is a little bit smaller. The pie is smaller. Some of the slices have moved around now. So before we were using this low redshift calibration, we completely got rid of that because we got rid of all those low redshift samples. But it's subsumed into the Pan-STARRS calibration for using this first foundation sample, because that's all on the Pan-STARRS system. So you can kind of combine these 2 and see that, all right, they're a little bit smaller, but not not significantly smaller. Some of the things that are a bit better are like the bias correction, where you're able to really track how you're selecting supernovae and able to make things better. So we've done well. This will get even better as we move forward and add those several hundred additional objects from SWOPE and the rest of the foundation sample. But we like this so much, we figured we could do one step better. So we started a new survey, the Young Supernova Experiment, which also uses the Pan-STARRS telescopes. We observe roughly 1,500 square degrees of low extinction sky. It's at a given time, about 4,500 square degrees over the year. That's roughly all of the low extinction sky visible from Hawaii. It's also an area, and ultimately the depth will be very similar to that of the dark energy survey. So similar area, 4,500 square degrees instead of 5,000, very similar depth. So it's a pretty incredible data set. Part of this is finding very young supernovae. We're finding roughly 1 every 2 weeks that are within a day of explosion. We just found 2 in the last week, and we're observing currently with Keck to follow those up. And we're going to, over roughly 3 years, observe over 10,000 type 1a supernovae in the nearby universe. Really, increasing the number on the Hubble diagram. And so here is just a very recent spectroscopic Hubble diagram. We have many more that are just photometrically confirmed. And this is just comparing 3 years of this foundation survey where we got roughly 180 supernovae, and then 1 year of this young supernova experiment where we have very similar numbers. This will improve actually a bit because we right now are throwing out a lot of things before the final photometry is set. So this is going to be really nice, and then we have thousands more coming when we use the photometrically classified supernovae. Okay, so getting back to our systematic uncertainty budget here, one thing you might have noticed is that this red slice here got bigger. This is related to the supernova model. So this particular slice is now the dominant systematic uncertainty. So we wanted to deal with that. we had to use this old way of calibrating the supernova light curve, SALT-2, and make some improvements to it. So this is work that has been recently published by Darcy Kinworthy, a grad student at Johns Hopkins. And what I'm showing here are the model light curves from SALT-2 in blue and SALT-3, this new version, in red. And so you can see that generally they're consistent, but then you'll notice some things like the error snakes are smaller for SALT-3, in particular for the I band. They're much smaller for SALT-3 in the red than SALT-2 in the blue. And then you'll notice we now have a Z band. So in fact, before, the rest frame I band wasn't even officially supported by SALT-2. You had to use an extrapolation of the model to include the full Sloan I. And now we not only get that, but we can add in the Z band. What that means is for something like Foundation, which was observing in GRIZ, we are effectively doubling the amount of data that we can use to fit our distances. An added benefit of this is if you look at the color scatter for these two models, the color scatter for SALT-3 is significantly better at all wavelengths that we're using. You can see in the dashed line where things were extrapolated before for SALT-2 and the dashed line now where things are extrapolated for SALT-3. This will improve even more. We're extending it to the infrared right now. We're hoping to go to the UV. We're going to add more data. Everything's modular and easy to retrain. So this is an incredible tool. If you haven't downloaded it yet, I encourage you to do so. Now moving forward, what we needed for that is, really building the SED, we needed to look at spectra. One of my grad students, Matt Siebert, was pushing into the Scapora database that he built up. In addition to having 5,000 spectra of roughly 800 type 1a supernovae, it has 56 categories of metadata, and that's incredibly useful for doing ad hoc queries. It's all based in Python, but you can do queries in SQL. It's really powerful. And through this, he's able to look at the average spectra when you control for all these different things of metadata. And so what he's showing here in red and blue are the spectra that you get at peak for things that have positive or negative Hubble residuals. In the top here is when you make no corrections for light curve shape or color or this host mass step. And you see differences in the spectra that correlate with things that we know, like the silicon ratio and stuff that people who study this in detail can figure out. But as you make these corrections, then the Hubble residuals change. And as you move down, you can see that the spectra look very similar. But there are some differences even after you make all of these corrections that we do to put supernovae on the Hubble diagram. And just focusing in on that final value, you can see here, you get all this different information so you can figure out how things are changing as a function of wavelength for things like the phase or the light curve shape. And I just want to zoom in on the spectrum, and you'll see that in this final Hubble residual plot that there are some significant differences, in particular in the velocity of this silicon line in the center of your plot here, and it's matched also with some other lines like the calcium features and even sulfur and things like that. If you using this, we were able to look at the individual spectra and see that when you have negative Hubble residuals, they tended to have higher velocities at all phases near peak. It's a subtle effect, but it's there at every phase. And if you look at the Hubble residuals as a function of the velocity, you can see a small difference between, a small but significant difference between these two data sets. And so this is something that we need to take into account going forward. Some of this can be done by improved light curve fitting, but it might be that we really need some spectroscopy here. Now, the underlying cause here it still needs to be investigated, but this is a similar effect to what we found about a decade ago, where we saw that the extinction and reddening seemed to look different for high and low velocity supernovae. We attributed this to a different intrinsic color, saying that we were making our reddening corrections incorrectly and biasing our distances. So wouldn't it be great if we didn't have to make these extinction corrections? And just as an example of what we're seeing here, if you look at sort of something with a lot of extinction in the optical, if you go to the infrared, you can reveal a lot. I know Bruno will be talking about this soon. And importantly, the uncertainties in your extinction here on the left is in the visual, here on the right is in each band, get significantly smaller too. The theory also, it says that the type 1a supernovae have smaller scatter in the infrared. So wouldn't it be great to go there if we could? This is very hard from the ground, but NASA is willing to invest a few $1 billion to build this incredible space telescope, the Nancy Grace Roman Space Telescope. This telescope is similar to Hubble in a lot of ways, but it has an enormous camera with a field of view that's roughly 100 times larger than what you get with Hubble. So every hour of Roman telescope time is essentially a large Hubble program, 100 orbits. That's going to be a fantastic game changer. And there's going to be a lot of cosmology done with the Roman Space Telescope. There's this whole plan to do it. I'm going to focus on the supernova survey. I'm the PI of a science investigation team for this Roman Space Telescope to look at how type 1a supernovae can be used to measure cosmological parameters. We've been working hard on this problem for a while. A large fraction of the telescope time is going to be pushed here. And we are finalizing some additional new simulations, but it looks like we can find maybe something like 30 to 50,000 type 1a supernovae out to redshift 3 with Roman in the infrared. When you make a Hubble diagram, these are bin distances here. You can get something like this. And this red line in the residuals is if you have W equals minus 1.05, so 5% different from lambda CDM. And you can pick that out by eye. This is going to be dead simple to really like distinguish some of these models. And we're really talking about like super precision cosmology. Now, the other heavyweight in the 2020s is going to be the Vera C. Rubin Observatory. On the left is a recent image. This thing is very, very close to being up and going. And this is just going to continue this trend of exponential growth in the discovery rate of supernovae. So here's what we have up to last year. And then this is what we expect from the Rubin Observatory through the LSST program, where we might be having hundreds of thousands of type 1a supernovae, hundreds of thousands of supernovae per year. And so when we look at this systematic uncertainty budget, with these different techniques of improved low Z samples, analysis tools like SALT3, spectroscopy, going to the infrared, having these large samples, we're really pushing in all of these different directions. And I really feel like over the next decade, we're going to have just exceptional measurements of cosmological parameters with type 1a supernovae. And with that, I'll just throw my conclusions up for a second. Maybe I'll be able to go back to them. And I'll just really point out to the people who did all the hard work here. So here's my team. This was before COVID, and so this is recent, of course, how we meet together. And they're the ones who are really doing all the work. So I'll stop there. Thank you very much.
Thank you very much, Ryan. It was so interesting, your talk, that we didn't warn you 5 minutes before the end, but you more or less finish on time. Thank you. And we call for them for questions from the audience.
Looks like Mario has his hand up.
Yeah. A fantastic talk, Ryan. Very exciting results and prospects for the future. I would only suggest that your red vertical bar for the Vera C. Rubin telescope, I think you should move it a little bit to the right, because due to the pandemic, we had to stop the construction of the telescope in Chile. for about 6 months. And we are gradually resuming the construction work. And it is supposed to start operations by the end of 2023. That's a small detail, but it's important to keep it in mind.
Yeah, yes, you're absolutely right. I'm very excited about Ruben, and it's unfortunate that it's delayed. Roman, it looks like it's going to be delayed a little bit too. That's sort of, I think par for the course right now. But yeah, Ruben's going to be fantastic, and although the observing strategy hasn't been perfectly finalized yet, there's a huge potential for supernova cosmology. And people who are very interested in this should weigh in on this. There's an organization in the US at least called the Dark Energy Science Collaboration Desk. There are also ways to do this if you're not in the US. But yeah, I encourage additional comments about that.
I have a question, but it's probably going to be addressed later on in the session. Is about a comment that Dan Skolnick made on the fact that he didn't find mass step term in the brightness of type 1a supernova correlated with all the other parameters, that he thought that these mass steps is due to the difference of dust in different galaxies. This is probably a topic of discussion. No? What
Yeah.
if you have a view?
Yeah, I'll just say that it's being looked at very carefully by multiple people. There's been indications that it is from dust. There are indications that it's not from dust. I think the general consensus, though, is that going to the infrared will help. So yeah, I'm very excited about Roman for that reason. And there might be some other ways to do really interesting science from the ground as well. Z-band, Y-band, if you can get it, those are probably a little bit better than what we've done in the past. So yeah, I'm interested to hear from others as well.
And I see Bruno also has his hand up.
Yeah, I wanted to ask Ryan. So Ryan, you have now all these local samples, and I look, your Hubble diagrams are scattered around the Hubble line. Do you see an improvement? Or in other words, will we hit sort of or whatever, an uncertainty that we can't beat anymore for the distances, the relative distances?
Yeah, that's a good question. So things have improved. I'll try to find the slide while I'm talking. The improvement is it's getting harder and harder to extract out in the scatter sense, the improvement. From the optical in particular, we think going to the infrared will be better, but we just don't have large samples yet in the infrared to really say much. And what I can say is that a lot of a lot of these new samples are getting to the point where the scatter is similar to some of the old infrared samples. Now that I think as we build up the infrared samples, they will get better.
Right.
And new techniques will also help. But yeah, it's hard. This is hard work now.
Yeah. I mean, if I look at this graph, you look at the individual uncertainties of your points, they're much smaller than what the scatter is. And so that would indicate there's either some systematics we don't know about, or, something in this.
Yeah, you're absolutely right. And some of this is, if I can get there, some of this is things like this very small difference for the velocities.
Yeah.
That's increasing the scatter a little bit. There's probably other stuff that we just haven't identified yet. But you're absolutely right. That intrinsic scatter means that there's some additional source of uncertainty that we haven't identified yet. And if we could remove it, that would be really great.
Yeah, excellent. No, it's great stuff. It's good.
So now it's time for Nora. Nora,
Yes, hello.
thank you very much.
I'm now sharing my screen. Is everything all right for you?
Yes.
Perfect. So, hello everyone, and thank you for the invitation. So, my name is Nora Nicolas, and I'm a second-year PhD student working in Lyon under the supervision of Michael Rigaud in the Cosmos group of the IP2I. And today I'm glad to be presenting our work on the redshift evolution of the underlying supernovae 1A stretch distribution, which has recently been published on ANA with the following DOI. Following what Ryan has been saying, in current cosmological work, we're building the Hubble diagram, assuming that the mean luminosity or absolute magnitude of supernovae is a constant with an intrinsic scatter. But we have some reason to think that it should be changing with redshift, and we'll see that afterwards. But this change with redshift could be coming from two main things that which could have an impact on our measurement of such a variation. The first would be the calibration. So that is to say that even if the luminosity is perfectly constant, we are limited by our capacity to measure it, as Ryan just showed. And the other main source would be our lack of knowledge about how supernovae 1A work. Even if we know that they are white dwarfs, the modeling is dependent on the nickel of the stars, which we can't measure which we can't directly measure. And on this, in this study, we've been working on the latter by trying to determine whether supernovae properties depend on the redshift, and to try to study the dependence of supernovae properties with the redshift. We studied the supernovae 1A stretches because it's an intrinsic property of theirs, whereas the color, for instance, heavily depends on the environment and the interstellar medium. So the first step was to work on a complete sample, free of instrumental selection effects, a sample on which we would be sure to have the stretch present in nature. For that, we used 3 surveys from the Pantheon dataset, so the SDSS, PenStar, and SNLS samples, to which we applied 2 redshift cuts, as can be seen on top here. The idea of the cuts is to withdraw from these samples the supernovae which could be affected by Malmquist bias, and which could be in a space where not all of the stretches can be acquired by a telescope. But so as you can see here, for each of these surveys, we chose 2 cuts. The one on the right, so the farthest one, is where we determined the limit should be for each survey, which we could talk more in more details afterwards. So it has a good statistic while giving us a supposedly complete sample, and it is called the fiducial sample. But because we want to make sure to be free from Malmquist bias, we also took more rigorous cuts, so the closest one for each of these 3 surveys, which are called conservative. So they only serve as a comparison to the fiducial one. And so for the rest of the analysis, the fiducial one will be the reference one. And as such, it will be in opaque markers starting 2 next slides, while the conservative results will be in transparent. And in addition to these no selection effects free sample, we used the SNF and HST data, which were already complete, and we made 1 big stretch sample from all these 5 individual surveys, as you can see in the cumulative histogram in a log scale for the redshift here. The stretch distributions are shown in this figure, with the redshifts also in log scale on the x-axis, and the cumulative histogram of the full sample as before shown above. And in this figure, we can already see that the supernovae whose stretch is over this -1 line seem to be always populated, while the supernovae under this -1 line tend to become scarce with redshift, keeping in mind that it is in a log scale, so there has to be gaps. It tends to have less and less supernovae between the low stretch mode. And this is the disappearance that we wanted to study, because if the supernovae indeed evolve, if the stretch indeed evolves with redshift and we can measure that, it would impact the correction we have on the luminosity of the supernovae, and thus the distance estimation. So, but in fact, this stretch evolution was already expected when looking at Rigaud 20. Indeed, this paper presented these two elements on the left and on the right. On the left, we have the stretch versus LSSFR values of 114 supernovae from the SNF sample, and the LSSFR is a tracer of the age of a supernovae. So it's called young if its progenitor was young, meaning that it exploded sooner than others, and it's old otherwise. So here we have starting at -10.82 of the log of the LSSFR, two types of progenitors. And we see that the stretch distributions seem different. It would be a single Gaussian for the young ones, so a normal distribution of mu1 and sigma1, and a combination of that same Gaussian on another low stretch mode for the old ones only. So it would have another Gaussian of mu2 and sigma2. So that's for the left part. On the right part, we have an analytic expression of the fraction of young stars, of young supernovae as a function of redshift, so which is called delta Z, the fraction of young stars. And on this plot, we see that as the redshift increases, we find an increasing ratio of young stars compared to old stars. So, for instance, the supernovae 1A at the end of the SNLS dataset exploded in an environment that was composed of approximately 85% of young stars, while the first one of the Penstar dataset exploded in an environment composed of approximately 50% of young stars. So with the evolution of the fraction of young stars as a function of redshift from the right, and the different distribution of young and old from the one on the left, we see that we indeed expect the low stretch mode of the old stars to disappear with redshift, being consistent with what we were seeing earlier on the plot of the previous slide. So thanks to these two things, we have a link between the stretch of the supernovae 1A and their environment, and the link between environment and the redshift, so we can analytically test the idea of this low stretch disappearance. So with the distributions we just talked about, it's easy to come up with the expected mean stretch at any redshift, with delta Z being the fraction of young stars, the expected mean stretch, so a bracket x1 of Z, would be simply the fraction of young stars times the mean of the young distribution, and being a Gaussian, that's just mu1, plus the fraction of old stars, 1 minus delta Z, times the mean of the old stars distribution, so being the linear combination of the two Gaussians from the previous slide, A being the ratio of the two Gaussians, of course. So the parameters describing the distributions have been computed using our complete 569 supernovae of our sample, and the graphic representation is shown here, where we have the mean stretch on the y-axis and the redshift on the x-axis in a log scale, on which we show the complete sample cut in 6 parts of equal sample size. So as you can see in the bottom of the bins here, alongside two things: the mean of all the data in orange, so which is constant, and our analytic model and its error in blue, line, and band. When we compare the quality of fit of our age drifting model versus this constant orange line mean stretch model, we find a delta chi-square of approximately 30, which indicates that our model fits better to the data than the model shown in orange. But of course, we could have chosen different models, and we did, and here's a few of them. We tested a model with 3 independent Gaussians for the age population. We also studied a model based on the Howell et al. 2007 paper, which only have 1 Gaussian per age population, on which we allow the drift to exist or not. And there are also different models who don't have age population differences, for instance, an asymmetric one or a Gaussian one, which don't include any drift because they tend to model the complete stretch sample. And for each of the drifting ones, we tested whether an evolving or constant weight was better. So to test the viability of this model, we implemented a suite of different parameterizations that are shown on the x-axis here, and whose quality of fit from our base model is shown on the y-axis using an estimator that penalizes the addition of free parameters, so to prevent overfitting. And so the full markers represent the drifting models with the delta z evolution we've talked about, while the open markers represent the constant models. The transparent ones, as we discussed earlier, show the results for the conservative sample. On the x-axis, we find some of the other models from the previous slide. So for instance, the Howell plus drift one and the Howell plus constant one, 1 Gaussian for each age population. The asymmetric one that includes only 1 asymmetric, and other constant models here, including our model, but with a fixed ratio of Young stars, the base plus constant. And what we read on this figure is that any model that doesn't include a redshift evolution of the stretch distribution is automatically excluded as a suitable description of the data relative to our base model. We're not talking about absolute modeling, but relative modelings, of course. For instance, the asymmetric one has 10 to the minus 6 chance to describe the data as well as our base model. So what would be the implication of such a modeling on current cosmology? To talk about that, we have to say that the stretch underlying distribution is not something new. For instance, the beams with bias correction, or BBC modeling, is a technique that uses per-sample asymmetric Gaussians, which was excluded on the previous slide, to correct data for selection effects, extrapolating what is missed after the redshift limit. On this figure, we represented first the norm stretch histogram in gray of the complete Penn-star sample with x1 on the x-axis. And on top of this histogram, we have 3 things. So first is the BBC modeling asymmetric distribution in green. We have a full line and band, which are our determination of these asymmetric Gaussian parameters. So it's a reproduction of the work done by Skolnick et al. And the dashed line represent the author's parameters. So they are very close to each other, which indicates that we might have gotten rid of selection effects with our cuts. So I remind you that we cut the data before selection occurs, whereas the BBC takes the selection effects to correct the sample. And then on top of that, there is our bimodal model. And because the amplitude of each mode depends on delta z, at low redshift in blue, The distribution favors the low stretch mode of the old stars, which are mainly at a low redshift, more than it does at high redshifts, which are shown in red, where we find younger supernovae. And then the mean distribution on the redshift range of Penstar is shown in the black line and band. So what we see here is that the asymmetric Gaussian goes through the middle of the bimodal distribution, overestimating the number of supernovae 1A at a stretch of minus 0.7 and underestimating it at x1 approximately equals at minus 1.7 in comparison to our base drifting modeling. Of course, it's always relative. So this means that the supernova bias corrected standardized magnitude estimated at a redshift affected by selection effects would be biased by an ill modeling of the true underlying distribution, because if we want to take into account selection effects and correct supernovae which are gathered after selection effects occur, but we correct them using a wrong underlying distribution, we won't correct them at it should be intended, and it would have an impact on the Hubble residual and thus the recovered values of W, for instance. With that in mind, our next steps will be to determine the impact of this modeling difference by using the SNNR package to simulate samples in which we include this evolving underlying distribution, which could also allow us to refine the assumption of having a complete sample. And it's an undergoing work with the help of Dan Skolnick and his PhD student, Brody Popovich. And we have good hopes that this could show an impact on the recovered W values. So the future of supernovae being directed at lowering the systematic errors, and with the future of supernovae cosmology having less and less statistical uncertainties thanks to bigger and bigger telescopes, we hope that this work will be of use for the community, and we wish to refine it using the latest series available. I thank you for your attention, and I'm looking forward to all the questions you might have.
Thank you very much, Nora. It was an excellent talk. And I don't see at the moment hands raised. Let me see. Let me come in a moment.
People are applauding.
I have a question. Nora, are you in favor to add an extra term then in the brightness relation of 1As?
In the what, sorry?
In the normal brightness versus versus x1 plus color in the normal relation between brightness and other parameters of supernova. You want
in
to add
the trip equation.
Yes, exactly.
I'm not sure it would be that relevant because the correction is already made using the stretch and color, maybe including more parameters like in the light curve fitting, like Sugar is trying to do, or with better templates with the SALT 3, as Ryan mentioned, more hot topics. I think that the modeling of the physics of the supernovae is more relevant in that case, and I haven't read that much on adding a parameter to correct. Well, there is the mass step, which we could discuss, but I'm not sure I would that much.
Okay. Yes, we can address this later on in the discussion. So perhaps it's now time for Mario to share the screen.
Yeah.
Thank you. Thank you very much, Nora.
Thanks.
Okay, I will try to share. Can you see, Pilar?
Yes, very well.
Let's see if I can go to presentation mode. Okay, here it is. Okay, well, good morning, everyone from this side of the world. Thank you very much to the organizers for inviting me to give this talk about type 1a supernovae and the value of the Hubble-Lemaitre constant. I will use this opportunity to show that the problem of H0 is not with type 1a supernovae. Well, ever since the discovery of the cosmic expansion by Lemaitre in 1927 and by Edwin Hubble 2 years later, there has been a continuous effort and controversy about its value. The measured values of H0 decrease over time from 500 kilometers per second per megaparsec, values reported by Lemaitre and Hubble, to values of between 50 and 100 30 years ago, and to an impressively narrow interval today between 67 and 74. This effort has not been without passion, to the point that some prominent astronomers like Alan Sandage decided to engrave the value of H0 on the frame of the license plate of his car. I took this picture in the parking area of the Carnegie Observatory office in Pasadena. It's interesting also to see the name of the car model, Intrigue. Okay, this narrow range of values could be considered a great success, were it not for the fact that the differences yielded by the different techniques reveal significant systematic errors, which cast legitimate doubt on the lambda CDM cosmological model. Today, I want to revisit one of the traditional methods, which consists in measuring the luminosity distances to galaxies in the Hubble flow from the very bright type 1a supernovae. The most recent results on the subject are by Wendy Friedman et al., calibrating the type 1a supernovae using the novel TRGB technique, which delivers a Hubble constant of an H0 value of 69.8 plus minus 0.8. And the other one by Adam Rees and his collaborators using type 1a supernova again, but calibrated with Cepheids, which delivers a significantly higher value of the order of 74. Well, this technique involves 3 steps. On the right, measuring distances to the supernovae from their apparent magnitudes, corrected for stretch or decline rate, or color, and other parameters. Calibrating the luminosities of the supernovae in nearby galaxies, either using the classical Leavitt law for Cepheid stars, or through this novel TRGB, tip of the red giant branch method by Wendy Friedman and Cepheids by Adam Rees and the SHOES project. And the third step consists in calibrating the luminosities of these 2 types of standard candles, the TRGBs and the Cepheids, using, for example, but not the only method, the distance to the LMC. And the concatenation of these techniques is what creates a 3-rank cosmic distance ladder, where all links are essential for the purpose of determining the value of H naught, and none is less important than the other. Today, I will focus only on the second and third rank of the ladder, leaving aside from the analysis the determination of the first rank by adopting the detached eclipsing binary distance to the LMC by Grigor, Pietrinsky, and collaborators. So we'll leave it completely out of the discussion. And for the second rank, I will adopt 2 possible routes: the 19 Cepheid distances published by the SHUS project led by Adam, and the 18 TRGB distances reported by Wendy Friedman and her collaborators. For the third rank, our strategy is to examine various datasets and prescriptions for standardizing the supernova peak luminosities. Having multiple data sets and methodologies affords an opportunity to empirically assess the internal consistency of the method, of the technique, possible systematic differences in the type 1A method. The selection of the methodologies for this work was an a priori decision, consisting in not modifying whatsoever the original analysis of the distant supernovae by their authors, and at the same time by consistently applying such formalism to the nearby supernovae. By the way, when I refer to distant supernovae, I'm thinking about the smooth Hubble flow up to redshift of 0.1, not the super distant ones that allow us to measure other cosmological parameters. So given this constraint, we can employ 6 prescriptions for the standardization of the supernova luminosities, which are shown in this table. And the first row, we start with the Calantololo survey, which was the first data set of digital photometry for type 1A supernovae, obtained by our group in the early 90s. In this case, we normalized the BVI peak magnitudes using the light curve width, the famous parameter delta M15 introduced by Mark Phillips. Although the supernovae were not corrected for host galaxy reddening, because at that time we still didn't know how to do it, we removed from the initial sample 3 supernovae that had clearly red colors at maximum light. So we had a color cutoff to eliminate suspiciously reddened supernovae. So we ended up with only 26, sample of 26 objects, which was super big at that time. Then we introduced, we include another methodology, which was the one presented by Mark in 1999. Mark used the Calantololo supernovae and expanded our original sample using some of the CFA supernovae. So he had a sample of 40 supernovae in the Hubble flow. And in his case, he normalized the supernovae using a quadratic function for correcting for the light curve width. And he also managed to include a host galaxy reddening correction using the color excess measured to these supernovae. And I'm not going into the details, but he implemented 3 different ways to measure color excesses. In 2004, a group of us launched the Carnegie Supernova Program, the CSP, from Las Campanas Observatory, which led to the gathering of very high quality optical and near-infrared light curves of type 1a supernovae, light curves in the Hubble flow with very stable instruments. That was certainly a very important added value with respect to the previous efforts, which obtained data with mixing different instrumental systems, making hard the analysis of the data. Well, using these, the first subset of the nearly 100 CSP supernovae, subset of 31 objects, Gaston Folatelli in 2010 analyzed these optical near-infrared light curves and improved the host galaxy reddening technique presented a decade before by Mark Phillips, and managed to normalize the peak magnitudes using the light curve width using a linear term. And again, he corrected the host galaxy reddening using refined methods to derive color excesses. In a couple of years later, oops, sorry about that. A couple of years later, Kuttner reanalyzed the standardization of supernovae in the infrared in a similar manner to Folatelli, but limiting the CSP sample to 24 supernovae, which were the best observed. Again, she applied a linear term to correct for decline rate or stretch, and again applied a color excess correction. Wendy Friedman recently revisited the determination of distances to the CSP supernovae using a sample of 99 objects observed in the optical and the infrared and the near infrared. She used the light curve fitter Snoopy, developed by Chris Burns. And here the normalization was determined using a quadratic correction for the light curve width or stretch. The light curve fitter that was used in that case is called Snoopy. And the technique also incorporated corrections for dust reddening in the host galaxy using the color term, and they included a host galaxy mass correction. And finally, we include in this study the method implemented by Adam Rees, Skolnick, and collaborators using 217 supernovae, including mostly the ones obtained in the course of the Carnegie Supernova Program and the CFA surveys. The optical light curves, in this case, were analyzed using the SALT-2 fitter, which delivers supernova peak magnitudes using a color and linear correction for the stretch parameter, but they didn't include a host galaxy mass term. In summary, we have adopted 6 prescriptions for normalizing the supernova peak magnitudes, which can be applied to different band passes. And overall, we were able to obtain 12 independent values of H0. For each of these 12 combinations, we adopted the 0 point of the Hubble diagram published by these authors. We didn't modify that whatsoever, as I said earlier. This 0 point is empirically determined by the magnitudes of the supernovae and the redshift of the host galaxies. Okay. Then we apply the same normalization, the same technique, the same prescription to the nearby supernovae, which have distances either with the TRGB or the Cepheid technique. And we calculate their absolute magnitudes here, corrected in the same manner as the authors did it for the distant sample. And combining this information, the absolute magnitudes calibrated with the TRGB or Cepheids, and the 0 point determined from the distant supernovae, we can solve for H0, as you can see here, in a straightforward manner. Okay, here are the results in one figure. You can see the TRGB results. Well, the Hubble constant is shown in the horizontal axis for different methods, shown in the vertical axis. And in red are shown the results for using the TRGB technique, and in blue, the ones derived with the Cepheid method. And the main results are the following. Well, you can see that there is a clear offset between both distributions. The TRGBs are shown in red and are systematically lower than the H0 derived from the Cepheid technique. Looking in more detail to each distribution, we note one discrepant value, the one from Folatelli in the J band, which lies significantly below their corresponding mean. The good news is that this problem in the J band, using the CSP data, gets solved or was solved by Kuttner 2 years later in the same band and using nearly the same data. She did a reanalysis of the CSP near infrared data, the same ones, nearly the same ones used by Folatelli. And you can see that the problem is solved, and probably there is a systematic problem with the Folatelli J-band value. So leaving aside the J-band Folatelli points, we obtain an average of 69.5 from the TRGB calibration with a standard deviation of 1.5. This is not the error in the mean, it's just a scatter of the distribution. And whereas from the Cepheids, we obtained 73.5 with the same scatter.
2 minutes.
Thank you, I'm finishing. This systematic offset is significant at the level of 2 sigma. And as was mentioned yesterday by several speakers, this is a direct consequence of the systematic difference of 0.06 magnitudes in the distance moduli calibrated from the TRGB and the Cepheid methods. However, this study demonstrates that if the second rank is held fixed to the Cepheid calibration, for example, the different formalisms and data sets used to normalize the peak magnitudes of the supernovae yield very consistent results. Most of the scatter among the different solutions can be attributed to the statistical uncertainties, amounting to 1.5 kilometers per second per megaparsec. And the same conclusion applies or can be drawn when using the TRGB method. Obviously, the error bars were higher in 1996 from the Calantololo survey and data, because there were fewer objects. And today, both the Rees and the Friedman solutions provide much more precise values for the Hubble constant. So in summary, this analysis demonstrates that type 1a supernovae can anchor the third rank to a level of 2% precision. And this is an internal agreement. This internal agreement yielded by the type 1a supernovae, either using the TRGB or the Cepheids calibrations, is remarkable, as it comprises light curves of increasing quality over time, starting with the Calantololo DDI sample carried out in the early 90s, various releases of the CFA project, and the most modern CST data set obtained over recent years with a very uniform photometric system, both in the infrared and the optical. So I will show this slide for you to read with the conclusions. Basically, I want to highlight the final point that this study demonstrates that supernovae have provided a remarkably robust calibration of rank 3 for over 25 years. Thank you very much.
Thank you very much, Mario, for this very, very wide and very deep explanation on the question of the different ranks. And I would like to ask the participants to raise hands for questions. And I also want to welcome Wendy Friedman, who is among the participants. Hi, Wendy.
Hello. I can unmute here.
I have a question, Mario. When you show the Phillips results, 1999, actually in the paper, he derives only the high value for the Hubble constant. He never did himself the comparison using the TRGBs, did he? Because at least
No.
not in the visual or the blue. You just took his results and tried for the TRGBs, didn't you?
Yes, exactly, Pilar. In 1999, the TRGB method was not available yet, or the TRGB data were not available, as is the case now. So at that time, both the Hamui 1996 papers and the Phillips 1999 used the Cepheid calibrations that were available to us at the time. And we were obtaining lower values of the Hubble constant of the order of 65 at the time, mainly because, well, the calibration of the Cepheids has changed over the past decades. So now I use the same technique that we use in the 90s, and I apply the TRGB and the new Cepheid calibrations, and that's what allowed me to derive updated values for the Hubble constant. And what I find it remarkable is that they are super consistent with the results derived later from better data.
Are you planning to publish these new results that you have derived by changing to the TRGBs? Because in your paper in 2021, I don't see them like you have published the feeds.
Yes, thank you for the question, Pilar. Yeah, the 2021 paper was published, and there is a table with the resulting values of the Hubble constant using both the TRGB and the new Cepheid calibration.
I see Saurabh has his hand up.
You know, Mario, excellent talk. You know, it's one of the things that, you know, we've been looking to see whether the supernovae can be to blame, and, you know, it's harder and harder to make the supernovae at fault. So I very much enjoyed your paper. So one question I had was, the supernovae that you can calibrate with the TRGB versus Cepheids can be different. So, the TRGB can use early type galaxies and the 1As in those galaxies. So given your results, how much room is there if the supernova samples were different that you would calibrate from TRGB versus Cepheids? How much room of a systematic error could you imagine there be? Could you say, oh, it has to be less than 2% or 1%?
Thank you for
the samples.
Yeah, thank you, Saurabh, for your question. Actually, I had a slide on this subject here. Let's see. I think this is the graph that is published in the 2021 paper. Here, we only show 9 methods to derive the Hubble constant using the Cepheid distances. And in this graph, I'm just showing these 9 cases, which are the ones that allowed me to, oh, sorry, no, I'm using the wrong figure. I don't know if I have it here. Well, I may not have it here, but there is another, oops, that's a very different slide. Okay, you can recognize that that drawing, Bruno. Okay, oops, I don't know what I did wrong here, but in any case, I took, I did the analysis using the same supernovae between the TRGB and the Cepheid technique. And I also recovered the same difference using the same set of nearby supernovae. I don't have the graph here, but it is published in the paper. And I concluded the same results.
Do you find the same results? I mean, if you go really farther into the redshift, if you go really deep into very high redshifts, you wouldn't find a, let's see, delta in moduli of 1As in a method and another method increasing, or is keeping the same kind of difference all the time that will imply having the same difference in the Hubble constant?
Well, I'm using the supernovae in the Hubble flow up to redshift of 0.1. I'm not going into higher redshift because then you get into the complications of measuring other cosmological parameters like the deceleration parameter. So I restricted the sample to supernovae far away in the Hubble flow, but not too far away as to have to consider deceleration corrections or acceleration corrections in this case. So that's what that was how I selected my sample for this study, and the second rank calibrations, namely the Cepheids and the TRGBs, which are very nearby supernovae.
I see Wendy has her hand up.
Yeah, just to follow up and add to what Mario is saying, and another way of looking at that is, so in the 2019 paper, we compared the CSP sample to the sample of supernovae used by the Shoes group, and you get the same result. Just echoing what Mario is saying, it's not dependent on what supernova sample that you use, the systematics, and whether you use a mass step or not. So the paper that I posted last week, which is based on a calibration now extending beyond the LMC and including NGC 4258 and the Milky Way and the SMC, gives a consistent result. And it, I think, again, highlights this difference between the Cepheids and the TRGB. That is where the difference is coming in. But both the statistical precision and the systematics, I think, have we've been able to isolate more that's where the issue is coming from. Nice talk, Mario.
And Wendy, now that
Thank
you
you.
are here, I always wonder on the percentage of error by the peculiar velocities that we have in the samples that you and Mario are using. I was having the idea that perhaps going to COMA with the James Webb Space Telescope and getting Cepheids there and TRGBs may also give us a confidence that peculiar velocities are not an important problem. And I think it's feasible, no? Now with the James Webb Space Telescope in the infrared?
I think so. The difficulty there, I think for TRGB, would be able to push out. I think we could do COMA, but the difficulty, of course, is that because of the issue of systematics, you really need high signal to noise data. For the Cepheids, the problem is that Cepheids are bluer than the TRGB stars, and to find the Cepheids, you need to look in a passband where the amplitudes of the Cepheids are large enough to detect the variability. And so Hubble has been a great facility for finding the Cepheids because you can look in a V band, the amplitudes are of order of magnitude. But when you get to the infrared, the amplitudes are only a few tenths of a magnitude. It makes it very hard to find the Cepheids, especially because the Cepheids are located in the disk, and so it's the red giants and asymptotic giant branch stars that are crowding them. So I don't think JWST is going to be a really good tool for pushing then out to COMA. It's going to be very hard to get accurate magnitudes for the Cepheids using JWST. I think that the ground-based telescopes may help in future, the ELTs. That I think should allow us to go out to larger distances. There's a method that we've been developing and some other groups at UBC using carbon stars. They're brighter and they are red stars, so JWST is a good facility for them. That method of using the carbon stars hasn't been as obviously as well studied as either the TRGB or the Cepheids, but they're looking very promising when we compare them, the distances we get using the luminosity function of a particular class of carbon stars. We get distances that are in agreement at a few percent level with the TRGB, for example, and they could go to COMA in principle. So I'm agreeing with you. It'd be nice to have a check of the supernovae, and because nothing goes out that far right now with the same kind of precision, but we don't have a good distance indicator yet that rivals the precision or the accuracy of the supernovae.
Mm-hmm. Thank you very much.
Pilar?
Yes. Yes.
Sorry, this is the graph I was owing to Saurabh. This is showing the comparison between the absolute magnitudes for using the TRGB calibration and the Cepheids, but all in each case using exactly the same sample of nearby supernovae to avoid the bias that Saurabh was mentioning. And you can see that for the 12 methods here, the difference between the two absolute magnitudes is always negative. And 0, by the way, is this red line. So the error bars are somewhat bigger than the comparison I made when using the Hubble constant, H0, but this is ruling out this possible source of systematic uncertainty given by the number of nearby supernovae drawn by each of these procedures or techniques.
Mm-hmm.
And I think to follow up on that too, so because we can go farther out with James Webb for the TRGB, we can get more calibrators for type 1a supernovae, including more ellipticals. So if there is a difference, these issues of mass steps, and I think, as we've heard this morning, you will understand the reason for this difference better, but going to the infrared is likely to be helpful in any case. That is something I think James Webb will help with a lot.
Mm-hmm. Okay, Bob, what do you think we should do for the coffee break? We should
take a few minutes,
1 minute.
perhaps. We're a little bit overdue. Well, 1 minute may be a little bit short for folks, but a few minutes maybe.
2 minutes? Okay.
2 minutes?
And
Okay.
then we'll have Bruno after.
2 minutes, really? 2? Okay.
How about I offer to start slow?
Hi, nice to see you, Bruno.
Hi, Pilar.
Maria, you are still sharing your screen, I think.
I don't think so, Pilar.
Oh, no?
I
Oh, no.
stopped sharing several minutes ago.
I'm sharing.
Okay.
Coming up. Excellent. Is everyone here? Shall we commence?
Yes.
I'll give you just a short 2-minute warning ahead of time. I think we're running a little
All
bit
right.
behind, but I think we're having really great organic discussion. We can sort of take that out of the later timetable for the roundtable.
All right. Well, I'll try to be good. So thanks very much. I was asked to talk about the near infrared, 1As in the near infrared, and this kind of forced me to go back to things that I almost had forgotten. And so I'll try to do my best to sort of cover what was happening here. This is a field that's young enough that you can actually talk about the history. And this goes back to the very first observations that were done by J. Elias and J. Frogel and people mostly at Tololo. And these are the first two papers with infrared light curves of type 1 supernovae as they were at the time. And so this is the very first thing. And in the very first paper, they had 3 objects that they looked at. And they came up, this is taken straight from the abstract. They had this remarkable sentence back here where it says the 3 sets of infrared light curves are very similar and their dispersion in absolute magnitude is less than the uncertainty in the relative distances of the supernovae. So infrared light curves of supernovae may therefore be useful as distance indicators within a few tenths of megaparsecs. So they recognize that right away. 3 objects, 3 is a crowd, as they say. The interesting thing is they say they may be good distance indicators out to a few tenths of megaparsecs. Well, as we'll know, this has moved on. So these are the first 2 papers, 81, 83. Then they had a paper in 85 where at that point it became clear that the type 1 supernovae are more than just one thing. And so they correctly said type 1 supernovae, again from their abstract, type 1 supernovae show that the light curves fall into 2 well-defined groups, and I'll show you more of that. And the light curves of the type 1 supernovae appear to have a dispersion in color and absolute magnitude of plus minus 0.2 magnitudes or less, and make them potentially valid for distance indicators within the local supercluster. So now they're going for the local supercluster, but this is all very, very local, of course. They realized this wasn't helping too much for the distance scale, but at least that was going. And so these are the light curves out of the this is the 1981 paper. And you see they recognize that there is this peak, but they also recognize that this peak is happening about 40 days, 30 days, 30 to 40 days after the peak in the optical. So this is relative to the B phase. And so they realized that there had to be a decline here. So there had to be a first peak, and this thing is the second peak. And just for the fun of it, that's their Hubble diagram. So this is distance in units of Virgo distance. If you take today's Virgo distance, this comes out to be about 40 megaparsecs. So if you're a gravitational wave person, you would now derive a Hubble constant from that one point, but that's what it is. And this is the magnitude, the H magnitude at 20 days after, so 20 days here, which they sort of thought was around the minimum. So that's their Hubble diagram. Peter Meikle sort of followed this 15 years later. This is now, more, well, it's a decade and a half. And again, this is from his abstract. He now has 6 supernovae, 6 similar supernovae. So he's already separating out the type 1Bs or 1Cs. And he finds down here that the infrared light curves of type 1A supernovae should eventually provide cosmological distance estimates that are of equal or even superior quality of those obtained in optical studies. So this is now 20 years ago. He was advocating that he was an infrared person, of course, but we should do more in the infrared. And so that's what this talk is about, even though I don't do that much anymore. So this is his set of light curves. He now, 98 BU sort of was the first supernova where we really could cover, or the first peak was covered. And we had objects like 91T, which sits up here. There's no, I think that's the single point here. And then you have these objects down here, which is 86G, which was recognized in 86 already that this actually is doing something strange. Anyhow, so that's the status then. Peter also compared the absolute magnitude in J, H, and K for these various different supernovae as a function of, at that time, delta M15. And you see that there is some scatter. After all, this is one full magnitude here. So there's some scatter, but there's also 86G. We know, today, mostly this would be separated out anyway as peculiar. So if you look at this thing, you have a fairly small scatter, but you have a very small sample. So I should say that most of the data until today, I think, that's still true. Most of the data is coming from the Carnegie Supernova Project. most of the infrared data, I should say, for photometry for type 1a supernovae is coming from the Carnegie Supernova Project and also from the CFA, which had a dedicated infrared program. So those are the two major data sets. And I'll show you several Hubble diagrams, and essentially they all show the same data. You just add more and more data. So here's now a data set that goes back to Mark Phillips, 2003. And you see you now get very nicely covered light curves. Very few you get at the peak. This is again about 2 decades ago. And so the cadences, the searches were not at the same level as they are today. And so it was difficult to get things before peak. You know, again, what you will see is that the infrared light curves all peak earlier than the B light curves, for example. So that's that was shown, but others had shown that too. This is now not going into the infrared. This is just using the I band, but even the I band light curves have a maximum before the B maximum. So this is from a paper that Gertrude Contardo did again around 2000. And so this is just a time difference here. The dotted line is the maximum, the B maximum, the phase of the B maximum that's set to 0. And you see that V and R are a couple of days later, but the I light curves peak 2 to 3 days before the B light curve. And that's true in the infrared as well. And so then to the 2000s, this is mostly the SCP doing this work of the infrared, and Kevin Krishunas was the one to point out, this is now, what's this, 7 supernovae. He pointed out that the light curves around the first peak, this is now the first peak in these J, H, and K light curves, are very uniform. So these supernovae look very uniform. The other thing that was shown as already today as well is that the absorption in the infrared, of course, is much less than in the optical. So it's about a factor of 5 if you use the Cartelli law. And so that removes a systematic that we have, and that's much discussed in the optical light curves right away, or reduces the systematics dramatically, essentially by a factor of 5. So this is, at this point, you know, this is about 10 years after the optical light curves, the standard candle picture of optical light curves of supernovae was abandoned because of Mark Phillips's recognition that the light curve shapes and the luminosities correlate. And we're back in the infrared, where people now say, well, but maybe in the infrared, these things are perfect standard candles. And so this is from a paper that's now by Burns et al. And this is just showing the delta M15 here, or SBV, this new color parameter, SBV, well, then new color parameter, how in the U band and the B band, V band, you have these very strong correlations out to, you know, fast declining supernovae with the luminosity, whereas you have a rather flat, mostly flat. And again, if you cut at something like 1.6 that people like to do for delta M15, you have a almost completely flat relation here. So your luminosity does not depend on the optical light curve shape. All right. So this is Kevin's Hubble diagram at the time, nicely populated, small scatter and J, H, and K, wonderful thing. So at that point, you just say, we need more statistics, whether that holds up with more supernovae. And so this is about 5, 6, 7 years ago. I had a student starting, and we had a European program where we specifically were targeting infrared observations. And there was never a synopsis of that program. And so I asked the student to collect all the data from that European program, and it turns out there were 3 supernovae, and there was just not enough data. And so we went into the literature, and the literature at that point was the Carnegie Supernova Project. And so we took all the infrared data from the CSP, and put it together. I just asked the student, just put them together, you know, match them up at the B magnitude or something, you know, use some distance scale, and then matched them up. And this is just the raw data matched up. And you see how these things line up very nicely. This is sort of down here, this is the scatter. It's sort of a sigma, and every day you just take the sigma here and you look at the scatter, and you see that the scatter, by not doing anything, we're not, these are nearby supernovae, there's no redshift correction, there's nothing, or peculiar velocity corrections, and you see that you have a very small scatter around maximum for these objects. There was a series of papers that Suhail Dhawan wrote. We looked at a number of things, but this is essentially sort of the summary out of this. The second peak, which is at between 25 and 40 days in the supernovae, shows up in many regular type 1As, in all regular type 1As. And as Dan Gleason has explained to us, this is an ionization effect in the atmosphere. So you go from doubly ionized iron to singly ionized iron, and that shifts, changes the opacity. And so also, all of a sudden you get an escape in the infrared, and that's shaping the second peak. And so you have a fairly, at the first peak, you have a very uniform light curve. Then these things sort of spread out. But then if you look at the back here, we looked at this in more detail. If you determine the slope of the decline in the various band J, H, and K, the slope in each of those is very similar again. So we sort of then thought that this structure in here, the structure of the supernovae, must be quite uniform from one supernova to the next. But something is shifting this peak around. And so the idea at that point then was, and also connected to this essentially, is that maybe this is an indication of the nickel mass. And so we, through ICRANet's law, we sort of kind of know, and Richard Scalzo has done a lot of work on this, that the luminosity, the bolometric luminosities in particular, correlate, or the nickel mass correlates with the luminosity. Makes a lot of sense. Again, ICRANet said this 40 years ago. So this second peak we then surmised could be sort of an indication of the nickel, the iron, really at that, at 40 days it's cobalt and iron, but really the original nickel in there. And so we looked at that in a little bit, and this is sort of the idea here. Max Stritzinger did this in his thesis. He determined nickel masses through ICRANet's law, really bolometric light curves, and so that was the distribution of nickel masses. This is now Richard Scalzo doing the same thing, but with the supernova factory data. Up here is the Chandrasekhar mass, and so you see that's a distribution. He correlated that with the Echecta mass as well, but you see that there's a distribution of nickel masses, distribution of the luminosities. And so what Suhail did, he correlated, so we looked at we calculated the bolometric luminosity for a small sample of supernovae, and then you look at the time when the second maximum occurs, and lo and behold, this correlates extremely well. So this is Y, J, and H data, and you see that J in particular, you see a very nice correlation. So so this is now a timing argument. You just count the days until you have the second peak in the infrared, and you know what the nickel mass of the supernova is. And so this was calibrated with what we call the reddening-free sample. So we took a sample of supernova with very small color extinction, calculated the pseudo-bolometric light curves, and then derived this. Okay, and then you can turn around and then you say, okay, if this works, there's a tiny dependence on the reddening on the peak of the second maximum. Depends really not on the reddening. So then you could essentially apply this to fully reddened objects. And we had a case that beautifully could confirm this. So this is 2014J. And because in this case, this was the first case where people could measure the gamma rays from the cobalt decay. And so you measure the gamma rays, you determine the nickel mass from that direct measurement, okay? And so we did the same thing. We just looked at the second maximum in the infrared, counted days, and this is the nickel mass that we derived through that system, through that method, with an uncertainty that's almost comparable. So what you can now do essentially, if you have sufficient infrared data, you can actually derive the distribution of nickel masses that are produced in the observed supernovae. Now you have to be careful on the selection criteria, but in principle that could be done now. So this is now I think it's the CFA data set. Avelino wrote a paper, and this is 15 years after Kevin said it. They said it was a bigger sample, and they said type 1H supernovae are excellent standard counts in the near infrared. And you see this here. So these are templates that they derived. And you see that let's take the J band here, around maximum. Here's the residuals down here. The residuals are tiny. So around maximum, these light curves are all doing the same thing, exactly the same thing. This is also true in H. So within the first few days, okay, around maximum, it's almost 0. So within the first few days, you can take any point here, any observation, and you will predict your maximum fairly well, okay? So this is, I think this is 0.25. So within 10 or 20 days, let's say plus minus 10 days around the maximum, you can actually determine the peak luminosity, the peak, sorry, of that supernova with a single measurement, more or less. And so that's the idea here, that you actually use the infrared, but not necessarily as a full light curve. It's better if you do a full light curve, but that needs resources, so you can think about this. But you have, this is again from the Avelino paper, you have a smaller dispersion here. You have a smaller dispersion with your infrared data than you do with any of the optical data. And that's not because of these light curve fitters. They're doing the best they can. It's just because the optical suffers from a number of things, because you have potentially a color correction, you have these light curve corrections, they all disappear in the infrared. And so you get a hugely reduced systematics. And I think one of the most important things here is you get a reduced systematics on the extinction law. All the other things you can fit with more supernovae, but the extinction law, as you've seen with recent papers, you beat your head against the wall time and again to solve that problem with the extinction in the optical. Now, if you move into the infrared, nature does it for you. And so you get away with this. So Suhail and Saurabh met each other in Munich at the conference, and they came up with this idea to say, well, why don't we do a fully infrared Hubble diagram? So only infrared data. And so that's what we did. They kindly took me onto the paper, but they did all the work. And so what you then can do, you can start doing these checks between the calibrator magnitudes. So the red points are on the right side. So those are the calibrated magnitudes. And on the left side, you have now the distant sample. As you see, that's not much beyond 0.05, redshift 0.05, but you have the distant sample, and you can compare those two against each other and see whether you have systematic trends. These the open circle ones are excluded because they are fast decliners, as you see down here. And so you can do these comparisons, and that seems to be working quite all right. Although there's still a significant scatter, and this goes back to the remark I made to Ryan Foley as well. The scatter typically is bigger than the individual uncertainty, so that's something to think about. And so that's the Hubble diagram that Suhail, Saurabh, and I put together. And you see here, so these are the infrared data. These are the distant ones. So the anchors are not shown, but these are the distant ones. And you see that they line up very well. These are 27 distant supernovae, and we had 9 anchors. The 9 anchors are taken from the SHOES sample. So they have the Cepheid distance taken from the SHOES sample. So there's 9 out of the 19 anchor supernovae that have enough infrared data that you can actually do this in the infrared. And these are 27 distant ones where you have infrared data to do that. Okay, so out of those 37 supernovae, we came up with uncertainties that are comparable to the 200 supernovae that the SHOES sample used at the time in 2016. So as I said, we have fewer free parameters. There's no light curve corrections. We didn't apply any extinction corrections. And so no color corrections. And so you do reduce your systematics. This is now the latest. This is from Johansson et al. This is now a combination of the CFA and the CSP sample mostly, and they added a few of their own. And so the total sample now comes up in H and J. Sorry, the labeling has disappeared. So this is J and this is H band, and you see that you get very nice Hubble diagrams out there. Now, this Johansson paper looked at something at the mass step that's such a worry in the optical, and essentially the mass step disappears in the infrared. Okay, so there's no significance. These are the two. You see the difference here in the dotted lines. There's a tiny, if there's a difference, it's certainly well within the uncertainty. So that essentially disappears. And this is also from that same paper. And so these are in the optical, these are the mass steps that you derive in these various filter bands, BG and so on. And you see once you come to J and H, this is consistent with 0. So that looks like the infrared is helping you there as well. So what I would like to argue now, and I know some of you are doing this already, but I think what we should do is we have these exquisite programs to do highly cadenced optical light curves in many optical bands. And we should use that to leverage the infrared observations from there, okay? So one thing is only the normal type 1a supernovae show this second maximum. The fast decliners, some of the fast decliners show it too, but they show it much earlier. And some of them don't show it at all. Okay, and so if you have essentially 3 points, you have a point when you discover the supernova around here, you do another observation, I don't know, 10 days later, and then you do an observation 30 days later, and you will know that this is a regular type 1a, because if it's not, it will be down here in your magnitude. And so you have a 2, 3, 4 magnitude difference between a normal type 1a, which has the second maximum, and any other one. Even a type 2 will be down here at that time. So with a few points, what you need somebody needs to tell you the phase here. So you need the optical light curves to tell you those phases here. But other than that, with just 3 or 4 points, you can actually 3 or 4 infrared points in addition to the optical points. You get exquisite distances, for example, as I showed you before, around peak. Any of these measurements, if you have 2 measurements here and here, 1 each, you know your peak magnitude to better than a 10th of magnitude. As I said, requires good optical light curves. And so the sweet spot program was trying to do this, or was using this. So there are these papers by Wyan et al. I think Sarup is using the same method with CIRA, with HST, to do some of the nearby supernovae and raisins, which Bob Kirshner was doing for several years, is doing this for more distant supernovae. I haven't seen any results of any of those, so I'm looking forward to what they have to tell us. But in principle, they're doing exactly this idea. And then there's a program that I know of, which is called FLOWS, which Max Stritzinger is spearheading, and I'll show you some of what's happening there. What I just want to put out here is the Euclid is going to do deep drilling fields. And so you will have, every so often, you have Euclid look at one spot on the sky for an extended period. I don't know, I can't remember how long it is, but you're bound to get 2 or 3 epochs in those fields, in the deep drilling fields, distributed over some time. So if you then have good optical light curves, then you can take those Euclid 3 points and put them onto the infrared light curves, and you get distances that way. And Suhail did this in his thesis. He sort of explored this, and you could, in principle, do the cosmology the same way as we've done in the optical, but much faster. And you don't have to change the Euclid observing program. That's their biggest thing. You don't want to have them point the telescope for the first 3 years. So FLOWS. So this is a program that Max Stritzinger is doing out of Aarhus. This is a cast of characters As usual, you have people who do the work. These are the ones where the arrow points to, and you have other people who just talk about it. That's me, for example, in this case. So I know what they're doing, but I'm not actually contributing in any sense for the hard work that they're doing. So the idea here is to restrict this to local samples, a redshift of less than 0.1. And right now, Max calls this a pilot program. So he wants to essentially assure that we can do these distances to measure a local H0 and maybe do peculiar velocities for supernova hosts. And so he would like to get distances down to less than 3% overall, if possible. This is done through several different observatories. So Calar Alto is involved in here. The NOT is doing a lot of observations. Luis Galvani is the key person for the Spanish telescopes and also for much of the data reduction. The ESA NTT through the ePesto Plus program gets some data. And then we're getting data from the Caucasus Mountain Observatory, which is the special astrophysical, which is located at the same place where the 6 meter is located in the Caucasus. And then originally we had VLT time approved, but there were no observations done because we weren't operating for a while for the last year. So this is unfortunately fell flat. And so the idea here is indeed what I said. You do sparse near-infrared photometry, and you then piggyback on optical light curves that other people are doing anyway. And so at this point, there's about 230, just under 230 supernovae, type 1a supernovae that have been observed. Most of them have just one single epoch. So they have multiple filters, but one single epoch. And you see the redshift distribution. Here are the different colors, the different distributions from the different telescopes. So you see the NOT is doing a lot of contributions. The Caucasus, the CMO, is providing quite a few things. And then, sorry, this is the regular one. And the NTT, the PESTO program, is contributing some supernovae as well. So this is the end of my talk. I think the infrared offers us a tremendous, a different angle on our problem, if you want. So we have different systematics. We have reduced extinction, which I think is, that can save you several papers if you don't have to deal with extinction. We have much more, the light curves are more uniform. And so the second maximum is a gift. We should take it as a gift. Some people say, we don't understand it, it's complicating things, but it's actually a gift because it helps us in understanding the 1As, but it also helps us in interpreting them. No color corrections. I said reduced, no. So whichever, if there is a color correction, it's really small. There presumably looks like there is no correction for galaxy mass. So many of these worries that we have with optical light curves fall away. Now, if you do the sparse photometry, you can still do all of these things in the opticals. You can independently use your optical light curves to do distance in cosmology, but in parallel, you sort of get a parallel track in the infrared that's mostly independent, other than the phase that you need to know. And so you can do the cosmology just as well with different systematics, essentially with many of these systematics reduced. And so, as I said, only a few light curve points are needed to do this. And if you then piggyback onto these major, huge surveys that are happening, CTF, YSE, we heard about those foundations, then you can, I think you can add actually a significant amount into our problem with the cosmology. So that's it. That's all I have to say.
Thank you. That was an excellent presentation.
So let me just stop sharing so I can see people. Yeah, thank you.
Let us have a look at the questions.
I see Wolfgang, I think was the first to have his hand up. And then Ryan.
Hey, I hope you can hear me. Can you hear me?
Yes.
Yeah.
Sorry. Wonderful. Thank you very much for the really nice talk, Ron. So I'm still new to like the luminosities because normally I sort of do spectra more. And I mean, in the optical, like the light curves or the peak luminosities have a factor of 10 difference for cosmology 1As. Is that roughly true?
Yeah, if you take the extremes, yes, it's more a factor of 2 or 3 for the more regular ones.
And so in the infrared, I mean, no, you showed the plot, but how much was that? It was difficult to see in the small screen.
Well, so the typical scatter is 0.15 magnitude at this point, and so sometimes, yeah.
10%. And so why physically? I didn't quite catch that. Why physically would that be? Well, what is it? What's the physics drive behind this?
I didn't give you a physical argument for this. We don't
know.
I
see.
As far as I know. I had this question on Monday when Ken was showing his models, and he's matching the light curve with luminosity relation very nicely. And I would kind of like to set him the problem to do the same thing for the infrared, where he doesn't have to find any, where all the luminosity should be the same. It would be nice to understand that. I don't know.
I see. Thank you.
Ryan?
So Bruno, I think this is fantastic, and I agree that the infrared is the way forward. But one of the concerns I've had when thinking about doing this from the ground is the calibration. And so, so Rob in particular has this raw program, and Raisin, doing it from space. And of course, Roman is going to do this. And I'm just curious, what are the hurdles there, and how do you overcome them for the ground-based infrared?
Oh, there are lots of hurdles. I'm probably not the right person to discuss them, because I know that there's a number of people that I showed you in the flows program who spend, well, the last 2 years thinking about these problems. And so there's any number of issues. As you see, we're using small telescopes. We're using a 2.5 meter telescope. Of course, these are bright supernova, 18th magnitude is sort of a typical magnitude that we're looking at. And so there's many things you need to think about. And yeah, I don't, I'm not fully into this to really know exactly what they're working on. But yeah, no, there are problems, of course.
Sora?
Yeah, thanks, Bruno. That was a great summary of and especially the history of the field. So yeah, I would say, I'm also very optimistic about the infrared. I thought maybe, I don't know if there's this new movie out called Luca from Disney. I don't know if I have kids, so of course we have to watch it, a kid. And one of the characters, the voice of caution that speaks in his head to try and not have him do.
Oh, this is Bruno.
This is Bruno, right?
Yes,
the voice of
yes.
caution.
My daughter said
tell himself Silencio Bruno to get over that. But so maybe I can be a little bit of the voice of caution. I mean, one of the things, like with Wolfgang's question, right? Why are they so standard? I mean, it shows up in Dan Kaysen's models. But one thing to remember is that the actual luminosity that's coming out, let's say in the J band, is some small fraction of the bolometric luminosity. And so you kind of worry that if you're going to pin everything to just a few % of the bolometric luminosity in this band, maybe that's worrying. Maybe it'll be more worrisome for high redshift or something else, for other applications. Yeah. And then the other thing is that there are a couple papers that came out, so including from the Sweet Spot program, so a paper by Kara Ponder that suggested that there might be, and there was another one, I think, using CSP data, that there might be a host mass effect. So I think that is not completely resolved. I certainly lean on the side hoping that there is not. It's not a big issue, but I think it's important to recognize that I don't think that's a completely settled issue.
Right. I think you're absolutely right. I looked at the Ponder paper quickly. I didn't. Yeah. It's not settled yet. I think that's right. But it must be a small effect. So yeah.
I have a question for you, Bruno. Thank you very much for the historical overview and for all these wonderful details on the infrared. I read some papers where it seems that the H band was a little bit better than the J band. What do you think about this?
So that that has, yes, people said this very early on. I don't think it has fully, the data haven't shown that fully. There was a long discussion over, I don't know, again, this is, must be 20 years, 15, 20 years ago, where there's a depression. If you look at the SCD of type 1As, then the J is actually low compared to the others. And so there's a depression in the spectrum. And that has been discussed for a while. And when I looked at this, this is a few years ago, I was on the fence because I didn't know whether I should take this, how much of a problem that is or not. So if you just do, if you do Hubble residuals, if you don't have anything better to do, then the scatter in the J band Hubble diagram is not any bigger than it is in the H band. But this goes back to what Saurabh has said as well. It would be good to understand this in more detail so that we, that we have more confidence in this.
Excellent. And shall we move on to our next speaker, Nandita?
Yes, thank you. I'll share my talk.
So Nandita is scheduled for a 15-minute talk. I'll give you a 2-minute warning as well.
Okay, for my, it said 20 minutes, but anyway.
Oh, okay.
Well, I will try to be a bit faster, I guess. Okay. Why do I not? Can you see?
Yes, that looks good.
Yeah. I don't know why I do this. Well, okay. So thank you so much for the invitation. And I'm going to talk about alternative way of measuring the supernova 1A distance ladder and measure the Hubble constant. I am a PhD student working with Marika Brancesi and Luca Izzo. Luca Izzo is present in the audience, and these are some of my other collaborators. So let's start. There is an arrow which is not letting me switch the slides. Okay, yeah. So this is a very, very quick picture of the Hubble tension. I'm sure we have, all of us have seen this. The various Hubble constant measurements measured with different methods in recent literature. And you see there is a clear difference between the values measured in the early universe and the late universe. And this tension, this difference has now reached more than 4 sigmas. And we don't know if it's new physics or systematic. So do we need to modify lambda CDM model to explain this, or it's just systematics in either of the measurements at the 2 ends of the universe? We saw amazing talks here and others that are trying to identify these systematics. And in this picture, in either of the cases, to refute the tension or to verify it, alternative measurements are very important that means to look at this problem in a different light and arrive at solutions before we can claim for new physics. So I'm going to talk about one of such alternative measurements. I guess speakers before me already talked about this, of course. So supernova 1A have been the most important probes to measure cosmological parameters. And the way they work is through a cosmic distance ladder approach, which Mario mentioned, that we have in the first step we have the primary distance indicators like Cepheids and TRGB that are to measure distances to nearby supernova 1A, and then using these you calibrate the luminosities, and then we move on to the Hubble flow to measure the Hubble constant. And but the way they work is they are yardsticks, so they depend on what you put in the previous rungs of the ladder, of course. And in this way, the calibration of the supernovae become very, very important, of course. So the value of the Hubble constant largely depends on, or significantly depends on this. And if we want to look for systematics, perhaps this is one of the places to focus on. Zooming in here, until recently, what we had for supernova calibrations was Cepheids, which is used by the SHOES program. But in this picture, there are a couple of questions that one can ask. One is, what about alternatives, which was, of course, addressed by, in one way, by Professor Friedman's group using TRGB. So what about other nearby methods of measuring distances? Do they give us similar values if used as calibrators of 1A? And secondly, the issue of complementarity. So we know that Cepheids are found in late type spiral galaxies. So they are found in a certain kind of stellar population. So what about supernova 1A in early type galaxies? Do they behave in a similar way? If we use a calibrator in early type galaxies, do we get similar results? And these are the two questions that my work tries to address. So by using surface brightness fluctuations or SBF as 1A calibrators, so as a first work, firstly, we want to measure the Hubble constant, see if SBF can be used as 1A calibrators, and what are the prospects of measuring H0. And secondly, we want to compare it with the standard calibrators used, so Cepheids. And why SBF is complementary, I'll show you that in a minute. So before I move on to calibration, I'll just quickly explain very simply how does SBF work. So SBF, as the name suggests, surface brightness fluctuations. It's a way of measuring distances in nearby universe. And the principal idea is simple, that if you have image of a galaxy, and if it's very, very close to you, it'll be more mottled or grainier, while if it is much farther away, it'll appear more smooth. So it's just, you see the CCD just a symbolic representation of the residuals on the CCD. So the fluctuations for a nearby image are much larger than those for farther galaxies, and this is what surface brightness method measures. So it measures the fluctuations which are inversely, which goes inversely with the distance. There are some important points that I would like to mention which are relevant to the work here. The way SBF works, it requires knowledge of galactic modeling and stellar population. So that means that it works well on those galaxies which are dust-free or have a more uniform stellar population they are more homogeneous. So it works well on early type galaxies. And this is why the SBF method provides us a complementary way to calibrate 1A as compared to Cepheids. Second important point is very much discussed in the previous talks, is about the reddening. Because there is less dust in early type galaxies, the reddening is definitely lesser as compared to the spiral counterparts. Thirdly, in terms of observational advantages, SBF does not require very deep photometry or resolved stellar photometry, while in Cepheids you need to resolve each and every star. And secondly, it does not require periodic observation, so it saves us a lot of resources. Fourth, SBF. So SBF can reach larger distances as compared to Cepheids. Cepheids has a limit of around 25 megaparsec, but with SBF, one can measure distances to about, so current distances are about 80 to 100 megaparsec, and with the upcoming instruments, especially JWST, it is expected that one can measure distances to about 200 to 300 megaparsec. So in this way, we definitely will augment the calibrator sample, because you reach a larger volume. And then, of course, we are having, as Ryan pointed out, hundreds of thousands of supernova detections coming up. So these are the things that are sort of to remember as I talk about my work. Since I want to calibrate, so one is with the SBF, I want to build a calibrator sample. So a set of nearby supernovae where the host galaxies have their distances independently measured with the SBF technique. So I used totally archival data. I cross-matched some samples and removing some outliers and providing some light curve cuts and filters. I compiled a sample of 24 supernovae whose host galaxies have the distances measured with SBF technique. And as I said, that I want to compare this new calibration with Cepheids. How do they compare? I also take the SHU sample, which is a set of 19 galaxies having their distances measured with Cepheid stars. So, and this data has been taken from Reese 2016 paper. So these are sort of two parallel calibrator samples that I used in my work. So I perform a parallel analysis on both of them. And see how they compare as calibrators. And of course, to measure Hubble constant, we need a Hubble flow sample. So for that, I take a portion of the Pantheon sample in the redshift range of 0.02 and 0.08. So the Hubble flow sample remains the same, and I use these two one by one and compare the results. So I take all these light curves. For light curve fitting, I just want to mention that I use Snoopy, which is written in Python for supernova light curve fitting. It performs K corrections and galactic extinction corrections built in. And what I constrain using these for each light curve is the light curve shape, which is parameterized here by this parameter called stretch color, and the B-band maximum and the color B-sweep. And then I go on to calibration. So I use a simple model. I do not use mask corrections as of now. So I use a shape correction and a color correction. And I model the apparent magnitudes of the calibrated sample such. So mu calib here is the SBF distances of the calibrated sample. So the independent distances of the calibrated sample. And then simultaneously, I have the Hubble flow sample where I write the distance moduli as function of redshift and Hubble constant. So I use these models and simultaneously I put them in a Bayesian framework. So my data and my models, and I fit for the nuisance parameters P0, P1, and R, and the Hubble constant. So I'll give the results. Now we move to the results. So with using the SBF sample as calibrator, I get a value of, and the Hubble constant, the Hubble flow sample, I get a Hubble constant value of 70.50 plus minus 2.4. And here you see posterior distribution of the measured Hubble constant compared against Reese et al. 2016 and 19 values. And then on the left is the Planck value from CMB. And here is the Friedman et al. Value from the TRGB. So the value measured with SBF calibration in this work agrees well, or is rather very, very close to the value measured with TRGB. And when I use the same analysis with the SHU sample, so replacing the SBF calibration with Cepheids, I get a higher value of 72.84. You see the red curve, posterior curve here, which agrees well with the Reese 2016 value. So it's good, but we see that with these two different rung 2, as Mario said, so rung 2, we get a Hubble constant, which is about 3.5% different. And we just wanted to look at it a bit closely. So we compare the distance moduli of the Hubble sample measured with these two calibrations. So here you see on the X, the distance moduli measured with SBF calibration, and on the Y, distance moduli of the Hubble flow sample measured with Cepheid. And here we see that the distance measured with SBF are sort of almost systematically higher as compared to those of Cepheids, and we found a mean difference of 0.07 mag, which corresponds to the difference we saw in Hubble constant. So at a first glance, we see that SBF calibration is providing us a longer distance scale, which sort of translates to that our supernova and early type galaxies intrinsically brighter. But this is not very straightforward thing to say, I guess. We definitely need more investigation here. There are recent works that discussed similar conclusions, but again, we need more work in this thing. The difference that we see in this work, of course, can be attributed to different environments because, as I said, the SBF sample, the calibrator sample, is mostly populated with early type galaxies, which have less dust, a different stellar population, while the Cepheid sample is populated with late type population and a lot of dust. So they have different environment, different progenitor properties, and this can cause the differences in the supernovas. So now this dependence of supernova luminosity on host is not something new. It has been, the corrections has been used for almost a decade now. So I tried to do that as well, just to see what changes, if something helps. So I put a linear mass correction with for the host stellar mass in our model with the shape and color. And you see the results here, how they change. So the white curve with the SPF becomes the purple one, which is almost overlapping it, and we see no change. For the shoes calibration, the red one becomes this orange one. So there is a slight change, but within the errors, there is no particular big change. Now, so this is a linear correction. In literature, there's also a step correction used, and I also tried that. So I use a step of a particular step threshold above which it's 0, the correction. And again, the SBF calibration didn't show any change as compared to no mass correction. While the shoes correction shows calibration shows slight change, but again, insignificant. So the conclusion here is that the stellar mass of the host does not seem to resolve or account for this scatter or this difference in the values. And this is where I think, again, a lot of work is going on, and we even discussed in the previous talks that how mass is affecting in different bands and so on. So maybe we need to find more parameters to explain this effect dependence on a host, maybe with surface brightness or age or some other parameter. Before I conclude, I just want to give a couple of updates which are really exciting for this work. So I did this work around a few months ago, and now we have new supernova 1A coming in, which in the galaxies for which we have SBF distances already. So there is 2020 UE and NGC 4636. There is 2020 NLB in M85. So we already have the data for these two and have the distances. There is a very recent one, 2021 QVVV in this in Galaxy NGC 4442, and the data is coming soon. It is still peaking, and all of this data is all these supernova are being followed up with the Young Supernova Survey, which Ryan talked about. And for these two, the first two, there will be soon a paper with me and Luca. So we hope it will be out soon. It has been sort of in delay with my thesis and stuff anyway. So there are a lot of new supernova 1A detections happening, and another interesting thing that came up recently is publication of surface brightness distances of new galaxies. So there was a paper from Jensen where they published distances of SBF distances of 63 galaxies out to 100 megaparsec, and 24 of these galaxies are supernova hosts. So they are useful for calibrating 1A. So it is basically doubling our sample right away, and we are already working to update our supernova sample calibrator sample. So we have a sample of 24, and these are other 24 galaxies with the most latest SBF distances that we can use to calibrate 1As. And I hope to see the results of this soon. I'm really excited about it. And now I would just give my conclusion. So I think when we started, one of the main idea was can SBF be used? And definitely this is promising, and SBF can be used as 1A calibrators. The H0 value from this work sits midway and agrees well with the TRGB. value. The host galaxies of the calibrator sample seems to affect the results, and the stellar mass correction does not seem to be the most the optimum parameter to account for this. So that's where we need more work. And of course, we have promising prospects coming up with the large supernova surveys detecting really multitudes of supernovae 1A, and the upcoming telescopes that will improve in every regard the distances, the 0 points, and the systematic errors and the calibration errors and so on. So yeah, I would like to stop here. Thank you so much, and I look forward to the questions.
Thank you for the excellent presentation, Nandita. We have time for questions.
Oh, sorry.
I see Saurabh has his hand up.
Yeah, I have two questions. I'll ask one first,
Sure.
and then maybe you can come back with others. So the first question is about the calibration of the SPF. I think for your paper, it was a lot of literature values. Is there any work on, consistently calibrating the SPF for all?
Yes. So the SBF used in my paper used the LMC distances from Friedman's paper, from Benny Friedman's paper 20 years ago, but now the new ones have used the latest LMC distance. So that's one thing that we can also. So we of course use the latest ones now, and for the previous ones we can move up, like sort of systematically move them up, because the difference between the older LMC and the newer LMC. The second thing I think you said about the calibration of the SBF, though. So in this work, the SBF distances used have been calibrated with the Cepheid, the 6 Cepheid galaxies from the HSTP project. But in this regard, so this is sort of a caveat, let's say, that there is, and it needs significant improvement. So there are proposals where TRGB can be used, and there are possibilities which compare well with this empirical calibration of theoretical calibrating SBF, which completely makes it sort of, it does make it a primary distance indicator. So you have theoretical with the theoretical calibration. So there are works going on, and then discussions going on, and let's see if we have them in the future. But right now, the calibration of the SPF in this work is definitely a caveat which needs improvement.
What about NGC 4258? Is there enough of a bulge or anything there to make that SPF calibrated?
Until now, no. Maybe something in the future.
I had a separate question if
yeah, sure, please.
So yeah, so for your third rung, the Hubble flow sample, I understand and I totally agree with why you did it, that you kept that fixed so that you can look at the difference. But I think maybe a next step, and especially what you're saying, like the host mass step didn't seem to resolve this issue. I think the next step may be to look at that third rung and then choose a Hubble flow sample that is better matched to the second rung. So for Cepheids, you want to choose a Hubble flow sample that is late type galaxies. But for your Hubble flow sample for SPF, I think you would want to make a more elliptical galaxies, make the stretch, the X1 or the color stretch distribution, the color distribution match between those two.
Definitely. So there are a few things that I would like to mention here. So firstly, I did not also publish this in the paper, and neither did I show here, but I did the same analysis with the CSP sample, and the results were really same. There was no difference. So I used both these calibrations on the CSP sample with significantly no different results. So that's one thing. Secondly, what you talked about cutting the sample or sort of differentiating between or making it more same or similar with the calibrating sample. We also tried that, and we are trying to either differentiate it with the mass or with the stretch values. These are the two parameters that we have been working on. The results are still under processing, but that approach seems a bit sort of arbitrary, right? Like you can't. So you have a Hubble flow sample and you cut it just to match it with the calibrated sample. Perhaps I'm missing something, but I find this approach very arbitrary to cut the sample right away, like just cut it. So is it maybe I can you can tell
I mean,
me.
I think you could argue it both ways, but I would say, you know, for instance, if you were using Cepheids and your calibrators are all star-forming galaxies, then someone could rightly say that having elliptical galaxies in your third rung, that's a mistake, because if there's any difference in the elliptical calibration, you know, the supernova standardization, then you're going to throw that part off, and you're not going to throw the calibrators off. So I think it is worth, you know, looking at the stretch and
definitely. We are already doing that, but then again, along with, so parallelly, there is the question that is it a good approach? Definitely, it's worth investigating and seeing the results, no doubt about that. But on a bigger picture, is it worth? I mean, is it a good approach to cut the sample?
I think in the future, you know, we're going to have thousands of supernovae, and it will be, I think it will be a good approach to, you know, pick the best ones, the ones that best match your calibrators, the ones that best match whatever selection effects go into the surveys. I think all of that will be in.
Yeah. Okay. Yes, that's true. Yes. Thank you.
Thank you. That was, oh, question.
We move to the last talk, and I think we'll have some minutes for discussion. We'll have some minutes.
Yeah, I think we'll have till 1:40 as previously, so folks can hang out and we can have a mini roundtable at the very end.
Hi everybody. So I think I'm on the last talk, so I'm just going to start sharing my screen. Can everybody see that? Okay.
That's good.
I don't think this should be too long either, so there should be plenty of time at the end for the roundtable discussion. So I just want to start by saying thank you very much everyone for the invitation to talk here. It's great to be able to talk about this measuring the Hubble's constant with inverse distance ladder. I've uploaded the slides online, so if you do want a copy, you can get them there, or please do just drop me an email here. So this was the paper where we published the results. The main reason I want to show it here is just to emphasize that there are many, many people involved with this, especially the first couple of lines of the author list. People were very heavily involved with this paper. So this was from the 3-year sample of the dark energy survey, which was, so this was published in 2019. Now my math is a bit rusty, but by my reckoning, I reckon that was about 20 years ago. So my math's a bit rusty, but that seems about right. I reckon it was probably about that long ago. So we observed a total of 329 spectroscopically confirmed supernovae, and all with spectroscopic redshifts, going out to about redshift 1. And all of our analysis was done blind. So we set up the whole analysis pipeline without seeing what the final results for Hubble's constant were. So we were looking at the shapes of the contours, checking our statistics, that sort of thing, but we didn't actually see what the value was. So just a quick spoiler warning, the value that we get from this when we unblind it, it's almost exactly the same as the Planck plus lambda CDM value for H0. We really did do this totally blind. When we unblinded, that's just sort of what it was. So, exceedingly close to the Planck value. I'd just like to emphasize, I'm certainly by no way a sort of Planck plus lambda CDM devoted fanatic. And I just, at the end of the talk, I'll just quickly show something just to kind of emphasize that, I'm really not kind of religiously adherent to that. It's just, we did the analysis, we did it all blind, and when we unblinded it, it came out, almost exactly the same as the Planck lambda CDM value. We've seen the plot a bit like this a couple of times before, and I think, if anything, this kind of really just sort of thickens the mystery here. So this is from ResetL 2019. So in this plot, they're kind of setting up, there's a bit of a kind of dichotomy here of the sort of, you've got the high values and the low ones. I don't think it's quite as clear cut as perhaps you might get from this plot, that it's only kind of late things and early things. But one of the things I'd like to emphasize with this plot, so obviously maybe there's kind of new physics that people are thinking about. But even if you just took the observations at face value, it's actually, I think, quite difficult to draw out a kind of coherent story which could explain all of those. Because even if you said, okay, there's something that no one's thinking about with the supernovae, then you still have the strong lensing results in that kind of high H0 camp. And then you might say, okay, well, that's maybe slightly lower and it's got the larger error bar. So maybe there's just enough wiggle room to make it all work if there was something with the supernovae. But I think, it is quite a, a convoluted plot now. And that obviously there's lots of great work looking at the physical explanations for this, but I think it's even difficult to say, okay, what's the kind of coherent narrative of the observations? So the inverse distance ladder measurement, it's this point here. Can you guys see my mouse coming up on the screen if I'm pointing like this? Does that come up?
That looks great.
Okay, so that's our point. Great, thank you. And that's really what I'm going to be talking about this afternoon. So really sort of how we got that. So this is the supernova sample that we were dealing with. So the points in red there towards the high redshift, those were new supernovae found and observed with the dark energy survey. And then the lower redshift ones, they are legacy supernovae, which we've included and kind of carefully worked into a coherent sample. So we've got a very nicely controlled, carefully calibrated redshift sample out to redshift 1 down to redshift 0.01. Okay, so a good redshift range there. So typically with the distance ladder, you start by calibrating the supernova magnitudes, with some geometry to, starting with parallax or something. But with the inverse distance ladder, the idea is that we start out at kind of far great distances, and then we work our way back towards redshift 0 to see what we get for H0. So instead of using parallax or something like that as the first step of our distance ladder, we really start with baryon acoustic oscillation. So we get basically some sort of angular distance. So in order to convert essentially a measured angle into some sort of more physical distance, we need to know, what is the scale of that angle that we're measuring. So we do use some information from the CMB, so that physical scale of the BAO. And I'll say a bit more towards the end of the talk about sort of why I'm confident that that's sort of pretty robust and what are some of the implications are for our measurements. So what we have is we have these BAO measurements there about redshift sort of 0.5, not quite up to 1. And they give us, in a sense, a sort of absolute distance measurement. And then we use the redshift, essentially the shape of the supernovae, to bring us back to redshift 0. So on this kind of plot here, where we have the distance modulus changing the Hubble's constant, essentially moving it up and down. So you can almost think of it as we kind of want to be moving that Hubble diagram up and down until it agrees with the distance measurements from the BAOs. I think one of the first big results to use this inverse distance ladder, it was done with the JLA supernova sample. And I think it's a really nice analysis. So these axes here, they're kind of a little unusual, but essentially it's a quantity which converges to Hubble's constant at redshift 0, and it doesn't diverge because you're having a redshift 0 in there. So these blue circles here are the BAO points, and then these crosses are the JLA, and they've essentially been calibrated so that they will go through the BAO points, and then you can work that backwards, and then they got a Hubble's constant, sort of very close with that kind of CMB plus lambda CDM value. So we thought it'd be really interesting to do this with the dark energy survey, and also with some slightly more updated BAOs, and see, are we going to get anything different? And of course, I've kind of spoiled the surprise, because you already know we basically find the same thing. But it's interesting to see that, with an independent set of supernovae and some slightly more updated BAOs. So I'll just say a little bit about something quite interesting that we did differently with our analysis over the previous one. The previous analysis used essentially a distance redshift model based on the Friedman equations. And what we actually do is we use a cosmographic model. And the advantage of this is essentially agnostic to the physics of the distance redshift relation. It's just a descriptive relation. So if you want to see how this works, if you look, we've got this is essentially the kind of the linear first order kind of Hubble's diagram 101 that you might write down, which is of course only true for very, very low redshifts. But we can do better by adding on extra terms here, so which depend to higher order on the redshift. So we can put, the deceleration parameter and high order things like that. So what's nice about this is that we can describe the distance redshift relation, but we're not imposing any particular models for, okay, dark energy is a cosmological constant or anything else like that. It's kind of just agnostic to what the physics is there. So this is our plot. So basically the equivalent of the plot that I showed you with the JLA. So we have the same thing on the axes. I got the redshift 0 on the left-hand side, so it's flipped around in that respect, but another way, it's the same here. So we can put the BAO measurements directly on this plot because we're looking at the distance there. And then what we do, we can see if we just extrapolated that back to redshift 0, we actually get a even lower value for Hubble's constant. So this lowest BAO redshift is about 0.15. So, pretty close to redshift 0. It does give us some constraining power, but when we add in the redshift, we can directly, when we add in the supernova, we can directly bring that redshift all the way down to 0. So here are our supernovae, and what we've done in the likelihood analysis is that we've found the best magnitude, which essentially you can think of it on this plot, gives us the best agreement in this region over here. And then we can fit to this combined data set, and we get this result over here. So we can take that redshift, so we can take that Hubble's constant all the way down from redshift 0.15 all the way down to 0.01 in a data-driven way using our cosmographic model, and we find almost exactly what Planck found. So the one point I'd like to emphasize on this, which we're asked about quite often, is some people have said, well, of course you're going to get the Planck results because you've used a Planck prior. Just what I'd like to say about that is that applying the Planck prior to the BAOs, it really kind of sets the scale over here in this part of the plot, okay? So it says, okay, our BAOs are going to have to be there. And then we say, okay, well, our supernovae are also going to have to be there. But once we've set that scale, it's really not doing anything for us to kind of the left of the plots over here. So, we perfectly well could have had a model that looks like that, okay? That goes through, the BAO where the priors is, and then, it goes up to an H0 of 72, 73, something like that. We perfectly well could have had that model. If these points over here had just been over here, that we'd have got a higher H0. It just so happens that the supernovae are just kind of down there, and we get the Planck result. So I can understand why people might say, okay, well, you've used a little bit of information from Planck, and wow, your result is almost amazingly close to Planck. It must be just because of that Planck prior. But really what it's telling us is that the supernova in this redshift range are behaving sort of exactly as you would expect from lambda CDM, and we don't see a kind of sudden tick up of acceleration. Personally, I think it's a real mystery. I'd kind of love to know the explanation for it, but all I can say sort of from a data-driven point of view is that's just what we get. We've looked into all the different kind of systematics which could have been contributing towards this, sort of cutting out outliers, looking at kind of shifts in our parameters, increasing our intrinsic dispersion of supernovae. And so what we've got on the top plot is the effect on the distance modulus, and then the bottom plot is the corresponding effects on our measurement of Hubble's constant. And there is some shift, but there's really nothing which is going to be getting you up to kind of 73 or something like that. So there are some systematic uncertainties, but again, even if they were all going in completely the wrong direction, it wouldn't explain it. There's just not really enough wiggle room. The last kind of couple of results I'd like to show, just from another paper looking at the inverse distance ladder. And what I like about this is that they were looking at different kinds of models for the distance redshift relation, and also different priors using priors from Planck or from WMAP on the BAO scale. And what they find is whichever ones you're using, it's essentially always telling you the same story, always getting a result which is lower than the distance ladder result. And it's kind of summarized a bit here in this plot from their paper. So, you know, the value for the BAO scale, it is slightly different if you use Planck or WMAP. There's just a little bit of wiggle room, depending on which prior you use. But actually, if you use the Planck value for the BAO scale, that actually moves you slightly further away from the Planck plus lambda CDM value for H0. So it's really not kind of helping to resolve the tension in terms of wiggle room there. And then, you know, we've still got the Rees results over here. So look, I do think it's quite a mystery. I'll just kind of wrap up with a few kind of take-home points here. And I think the main take-home point is not just from our analysis, but really, I think any analysis looking at a kind of inverse distance ladder, that it's consistent with the Planck plus lambda CDM, not the conventional going outwards distance ladder. So again, this is slightly kind of above my pay grade here. But what I hear from the kind of CMB community is that the value of the BAO scale, it's really kind of robust to any kind of late time cosmology. So if there was some kind of weird late time dark energy kicking in and giving you a high Hubble's constant, that's not affecting what's going on with the measurement of the BAO scale. And again, I think the way to kind of summarize this point is that there's just not enough wiggle room to kind of sweep this kind of under the carpet in terms of any kind of uncertainties. You know, there are some uncertainties there, but you know, maximum you might be saying, okay, taking this from like a 5 sigma tension to like a 4, maybe a 3 sigma tension, but it doesn't make it go away completely. And that the last kind of take-home point I want to make is that, you know, we used a cosmographic distance redshift relation. The JLA paper used a kind of Friedman equation with some extra terms to account for differences, and then that paper from 2019 I showed you used different models again, and then also using priors from WMAP or Planck. It seems robust to all of that. So it's not like the tension is a Planck thing, not a WMAP thing. It's more of a kind of CMB thing, I think, would be the takeaway. And I think just the last slide, I'd like to finish on just a little bit of kind of speculation. And I just think that the point I'd like to emphasize is that it's difficult to stitch together a story just even through all the observations. Okay, you know, if we wanted to say to the kind of theorists, okay, here's what we would like you to explain, we kind of don't quite have a coherent message of all the observations for the theorists to kind of start thinking about for their explanations. My impression would be that that's suggesting that there might be several different observational effects. So maybe something going on with the supernova, maybe something going on with the strong lensing, but it's probably not just one magic explanation which will answer everything. And I guess maybe this is kind of increasing one of the biggest questions, you know, are the H0 tension and the sigma 8 tension related? I mean, I think everyone would love to have one neat explanation for both of them, but you know, they might just be completely different phenomena. I think we just need more data. So the very last thing I'll show here, I did promise that I was going to kind of try and convince everyone that, you know, I'm not a kind of Planck plus lambda CDM diehard. So I'd just like to show a plot. This is from a kind of old paper in 2013. So when we were actually looking at sigma 8, so comparing Planck predictions for sigma 8 and peculiar velocities, two measurements from redshift space distortion, so measuring the peculiar velocity with galaxy surveys. And what we found here was actually a kind of disagreement. So what the observations were telling us is a kind of lower sigma 8 than you would expect from Planck. So, you know, Planck has been fantastic. CMB tells us lots of stuff. And sometimes what we go out and see agrees spectacularly, as with the inverse distance ladder, and sometimes it doesn't. So I guess that's a kind of, it's not exactly kind of wrapping up everything in a kind of neat, tidy bow that explains everything. So I guess it's a good job. We've got a kind of bit of discussion roundtable after there. So I think that's all the stuff I'd like to show here. As I said, the slides are online, so please do feel free to download them. I think we've got a bit of time for questions, or going straight, if we want to go straight into the roundtable discussion, that's fine. But please do just drop me an email if you think of any questions a bit later, or anything you didn't get a chance to ask here. But for now, I'll just say thank you everyone for listening.
Thank you very much for this very interesting talk. I'm looking at the hands raised. Wanna see? I have a question for you.
Sure, yeah.
I mean, in principle, isn't it possible to get already directly the distance to alignment alpha, or kind of a galaxy distribution at different redshifts as in Einstein in the first papers, where the Hubble constant was also a possibility to derive directly without having to link it to the Planck data, just geometrically?
Yeah, I think in a nutshell, that's kind of what everyone would love to do, to kind of just completely decouple from the CMB. So I don't know quite enough about BAOs to say exactly, but I think the most promising way to do that, I think it might be possible with basically the Alcott-Paczynski effect. So essentially, with the BAOs, you can measure a kind of angular scale and then a kind of redshift scale where you're measuring the BAOs. And if you have your cosmology correct, then the scale in that direction should be the scale in this direction. So even if you don't want to say, okay, I know what that scale is, you can say, okay, if my cosmology is correct, then they should be equal. I think in principle, that assumption would be enough, that you could use the BAOs to anchor an inverse distance ladder without any priors from the CMB. Of course, it would make all your constraints a lot softer, but I think in principle that would work. Certainly if someone from the BAO kind of field said, yeah, that totally wouldn't work, I would defer to them. But I think in principle, that would be the best way to go. And I just think what you need for that is just the kind of essentially kind of cosmic variance limited BAO survey to really be able to do that. So I think that will get there. I think at the moment, it's not at the level where any constraint would be kind of sufficiently informative that it would really kind of contribute to where the source of tension is. But yeah, I think that's absolutely the right direction to be thinking about taking this.
Thank you. Bob, do you think we should share that slide with the questions?
Yes, let's go ahead and.
Yeah, shall I just stop this this sharing here?
Oh, yes, I don't think there are more questions that I don't see any more. I think we are having a few minutes left, and I think perhaps the specific questions have already been answered by the different speakers, because we had a very good discussion after the talks. It was very deep discussions on the presentations. So, well, Mario suggested to raise the generic questions as generic as whether H0 is a problem due to supernova, due to the first rank, or is the local universe special? In some way, we have already answered some of those questions. But if you have papers in mind that may be relevant to this discussion, please go ahead and mention them or express your thoughts about those questions. Also, if you want to go to one of the specific questions above, this is also very, very interesting.
I can jump in if you like and maybe address the second question on the difference between the Cepheid and TRGB distances.
Okay, yes.
The 0.06 number came from the Friedman et al. 2019 paper, which was just a direct comparison of the distances measured for the galaxies in common that all have TRGB, Cepheid, and supernova distances. And so that's the mean difference is 0.06. The 0.14 is what George Estaffiou raised in his talk yesterday, and he describes in his, what he called his lockdown paper. And that's if you calibrate with respect to the Large Magellanic Cloud alone. So you don't add in the Milky Way and NGC 4258, and that somewhat alleviates the difference in the overall value of the Hubble constant that you get. And so I think the thing to be said about that difference, whatever it is significant for the whole sample. You know, there's at least a 3% effect, systematic. And we need to understand where that difference is coming from before we attribute the tension to early universe physics. I think, you know, what has come out of the talks in this session, the mass, you know, the jump mass effect for supernovae is not going to be large enough to explain it. The difference in supernova samples, it's not coming from the third rung. I think many people are seeing this from different points of view, but the local calibration, and that includes the anchors, so the distances to the galaxies like the LMC 4258 and the Milky Way calibrations. There are still uncertainties there. Again, everything shifts depending on the absolute calibration. We know how to measure relative distances. The absolute calibration is hard, and that is what's driving this tension, and we need to understand where it's coming from. I just wanted to say that, you know, I think the point that we just heard about the BAO from Ed and supernovae, and the fact that the prior on BAO, you know, if you set the sound horizon or drag, would have allowed for a larger value of the H naught locally, is an interesting point that doesn't often get emphasized. It could have been much different, but the supernovae are constraining it to stay low. So I think, you know, these are all really interesting questions. But I want to emphasize again, it's not simply a fact that the local measurements are giving a high value of H naught. The tip of the red giant branch is consistent with the CMB measurements and the distance ladder.
Thank you very much, Wendy, for the answer.
Yeah, I just wanted to ask Wendy a question. So, you know, you said that comparison was made for TRGB and Cepheid hosts, also that hosted supernovae. Could you remove supernovae for the equation? Are there more galaxies that have both Cepheids and TRGBs that didn't have a supernova, but you could still do the TRGB versus Cepheid check independent of supernovae?
Yeah, so that also, you know, if we look at the nearby sample, galaxies that are closer than those that are host to type 1a supernovae, the agreement is excellent. So for nearby galaxies, they do really well. If you calibrate based on the tip of the red giant branch, using minus 4.05 as the absolute magnitude of the tip of the red giant branch, and with the current Cepheid calibration. And the discrepancy comes when you go out farther. So that's not surprising. The measurements get more difficult. And so if we were to say, okay, well, let's match to the Cepheids, then you don't get the good agreement nearby. So it's you know, you can't have it both ways. And so, you know, that discrepancy is coming as you move out into the realm of HST, where we can measure distances to supernova 1a hosts.
So does that point away from the anchors and more towards the HST, photometry, and all those effects in this?
I think it does. I think there's still uncertainties in the, for example, in the Milky Way, how well known is the 0 point, for example, of the Gaia EDR3 parallaxes. Those uncertainties are still in play. I think the Gaia people involved in the Gaia analysis, if you look at, for example, background quasars or look with respect to the LMC measurements where you can smooth over them, there's a variance. And so depends where you're looking in the sky. And the Gaia corrections themselves depend on the magnitude of the star, the color of the star, the position in the sky again. And so I think as we get better Gaia parallaxes in DR4 and DR5, those kinds of things will straighten themselves out. In terms of 4258, there's one maser galaxy, right? And so the TRGB and the NGC 4258 distances agree really well. The Cepheid doesn't. If you calibrate with say, the LMC and you measure the distance to NGC 4258 using Cepheids, you get a different answer than the geometric distance to that galaxy. So that again points to some issue in the Cepheid systematics, whether it's metallicity or in the case of if you fit, for example, you use the Milky Way Cepheids and you determine the distance to NGC 4258, then in that case, you don't have a metallicity difference. So you ought to be, you should get a consistent answer, but you don't. So metallicity is not the issue there. So I think there may be two parts to this. It may still, there are issues in the anchors and in the nearby galaxies, but the more that I think we get better data, the less I think the issue of interesting early universe physics becomes.
See, Nandita has her hand up and Ryan afterwards.
Yes, thank you, Mario. Thank you, Robert. So I would like to sort of a little bit just chime in for the fourth question and also kind of add to the discussion from Professor Friedman. So why SBF has SBF without so direct measurements of Hubble constant with SBF is giving a different value or higher H0 value than supernova when you calibrated with SBF. So one thing here is that, for example, for mu Cepheids and TRGB, there are common galaxies that have distances with both the techniques. But because SBF and Cepheids are sampling different kinds of galaxies, for the sample in our work, we did not have a significant number. So there were only 2 or 3 galaxies that had both the distances measured with SBF and Cepheids, so it was not significant to compare them directly to say if there are distances, if there are differences in the coming from the lower from the calibrated sample. However, what we could do was to compare the calibrated distances for both these samples, and I just want to share my screen for quickly, if that is possible.
Sure.
If you can allow me to.
Oh, I see.
You can allow me to share just for a minute.
Absolutely.
Thank you. Okay. So do you see this plot? This is from my paper. And this is a plot where we compared the distance moduli of the calibrator samples. So the 2 calibrator samples, this SBF sample and the SHOES sample. But the distances to these supernova are measured with the calibrations from SBF and SHOES. So there is a little bit of redundancy, but as well as the comparing effect here. But we see that with the nearby sample, with the calibrator sample, there is no systematic effect that we saw with the SHOES sample. So again, as I said, so there are of course a lot of things to improve and systematics to study, but from what we saw here, it appears that the difference when you compare SBF distances or SHOES distances in the nearby regime, that there's no difference. However, the difference is coming on when you calibrate. So it is the supernova that may be so the host effect might be the causing the difference of Hubble constant between measured with SBF calibration and Schuss calibration, because that systematic effect here we don't see with the local samples. So it is because we don't have a common sample to compare, it's a bit difficult to comment on why SBF direct distances with SBF are getting a higher H0, but at least we try to do this investigation the least we could do with the present data, and it does seem like the discrepancy comes from when we do the calibration, so when we are calibrating the luminosity, at least in this work.
Ryan?
Well, I wanted to ask kind of a pointed question, because I think we have the exact right people here to answer it, which is that the 1A dust seems to be weird, at least relative to the Milky Way. You see like, low values of RV. That also seems different from most extragalactic sources that we can measure. It's different from what we see for core collapse supernovae. A lot of different things are just different. And the Cepheids also seem to, generally give RVs of around 3 or something. But what if that's wrong, or something's wrong, right? So what if the Cepheid dust is like the 1A dust, or the way that we're calculating dust is wrong in one or both of these ways? What happens there?
So, these are things I think we do need to think about. I think the first thing to be said is you want to be comparing apples with apples. So if the dust, at least on average, is the same in your calibrating galaxies it is in the galaxies that you're trying to measure, then you're probably going to be okay. But something that we all need to keep in mind, of course, is that we're assuming a universal dust law. We know in the Milky Way that different sight lines that you measure different RVs, but again, if on average it's the same, then you're going to be okay. In the case of the Cepheids, and I think also for the supernovae, you have the issue that you need to worry about. There's a period luminosity temperature relation for Cepheids. That's the scatter in the PL relation. It has an intrinsic reason. You can't just minimize the scatter. There's a physical effect there. And what you do in the observational plane is you measure period luminosity and a color. Now the color, you need to correct for dust, which is an extrinsic effect. You need to correct for, you don't know what the intrinsic color of a Cepheid is. So there's some beta term that's a color term. And then you worry about whether there's some sort of metallicity effect. And so, there's this using H2 regions as a proxy for the Cepheid metallicity, and you have another color term. Those even could have different 0 points, but they're all lumped together generally. And so, I think when we talk about measuring a 1% Hubble constant and comparing with the CMB, we just have to keep in mind that there are systematic effects that if the reddening law is different, that could have some effect at the percent level. I don't think, if you were looking for 5% accuracy, I think we've shown these distances agree really well locally. We're not talking about a 5% effect, but the kinds of systematics that could come back and bite you when you're trying to get 1%, these are the kinds of things that would do it.
Do you think that we can learn something from the people that have looked at the dust evolution through redshift, and they were also involved in studying the Planck CMB at the infrared and the dust at those very high redshifts? I mean, they may have looked at the whole evolution of dust in different galaxies.
I said to make one comment, at least for the Cepheids, I think, Ryan, they moved for the mean magnitudes to be in the H band a while ago now. So at least some of that may be mitigated. I fully agree that there are at least 3 effects that, when you described there, that are being mixed together with one coefficient. So who knows, certainly at 1%, that's a big deal. But, that's the thing we want to do with the supernovae, right, is to also go to the infrared for the dust law.
Yeah, I think, just to hit on one of Wendy's points again, is just if you measure RV for a sample of supernovae, there is a decent amount of scatter. That probably is the same as well for just galaxies in general. And then if the Cepheid hosts are somehow different from everything else, that could be particularly troublesome. So I don't know. I agree. I think there are ways to mitigate this, but it's a sticky problem.
Yeah, the infrared is definitely the way to go, and the thing you have to keep your eye on there is the image resolution that you get, because if you then are worried about crowding and blending, you're trying to correct for reddening, you're trying to correct for metallicity, and you're doing those in optical band. If you're correcting for reddening, say, and with optical bands, which is what the shoes group do, and then look for a metallicity effect in H band, but also your more metal rich regions are going to be more crowded. There's a degeneracy there that it's going to be hard to break. So image resolution really matters, and that's hard in the infrared.
We don't know when we are going to be cut, but I would like to thank all the speakers for their fantastic talks. And I just have a question for Wendy about the carbon stars. I wonder how much improvement do you foresee on the distance to be obtained by the carbon stars method in comparison to the TRGBs?
So they're looking very promising. So this was a technique that was really brought to bear by Nikolaev and Weinberg in a paper that they wrote on the LMC a couple of decades ago. And so there were two, one in 2001 and 2001. And what they showed was that if they isolated a sample of stars in the J band, based on their J minus K colors, that these carbon stars had
Okay, recording is stopped, I believe.
It looked like I kicked out somehow.
We didn't hear you very well.
I think there might have been a bandwidth issue, but perhaps something about the paper from 20 years ago was about where it slowed down.
That's where it slowed down. Okay, so what Nikolaev and Weinberg were able to show was that if you use the luminosity function of this particular class of carbon stars with a narrow range in J minus K color, they could measure the geometry of the Large Magellanic Cloud. And that agreed with measurements from Cepheids and other ways of measuring the geometry. And you wouldn't be able to do that if there were systematic effects like reddening or the different ages of populations or metallicity. And so it appeared very promising. And so Barry Medora and I started to explore where there were ground-based data for nearby galaxies in J and J minus K. How did that hold up in comparison with things like tip of the red giant branch? And it holds up remarkably well. And we went into the HST archive. We have another paper about to come out, and it also, compared to the TRGB measurements, looks very promising. So we just got time. I'm very excited about this with JWST to do measurements in the same galaxies. We'll do TRGB, we'll do Cepheids, and we'll do the carbon stars. So to answer your question, quantitatively, we'll have a really good answer to that question, because we will do all of the same objects and see how well it does. But so far, it's holding up really well. It looks very promising. And they're brighter, and you need a single observation for the reasons Nandita pointed out in terms of overall efficiency. We don't have to measure periods, although if we get more, they are also variable, these stars. We can bring down the dispersion by having some time coverage.
I think before we get cut, many thanks to everybody. Many thanks, Wendy, for joining us in this session. It has been really great to see everybody's face again after these years without conference. And I think we should stop before they cut us.
Maybe it was a
Thank
hint.
you.
Yeah.
I want to say
Thank
bye
you.
to everybody. Bye.
Thanks to everyone for organizing this.
Bye-bye.
Great.